Hello there, and welcome back to Beyond the Cosmos, where curiosity takes the shape of a gentle question and science moves at the pace of a slow breath. Tonight, we are going to explore something that sits at the very edge of what astronomers have been able to map and describe. Something that, when you first hear about it, sounds almost impossible. A region of space so empty, so vast, so stripped of the usual furniture of the cosmos that it challenges our basic picture of how the universe is put together. We're going to wander slowly and carefully into the largest known void in the observable universe, a place called the Boötes Void. Before we set off together, I want to take a moment and ask where you are right now. Perhaps you are lying in a dark room with the curtains drawn, the sounds of the street fading outside. Perhaps you are sitting in a chair with a warm drink, the evening winding down around you. Maybe you are somewhere quiet and rural, and if you stepped outside right now, you could see a sky scattered with stars. Or maybe you are in a city where the sky glows orange with reflected light and the stars are mostly hidden. Either way, wherever you are, we are sharing this moment, and that is its own small kind of wonder. If you find this slow, thoughtful kind of science calming or useful, it would mean a great deal if you tapped the like button or subscribed. It helps other people who need a quiet voice to drift along with find their way here too. Now, settle a little deeper into wherever you are. Let your shoulders drop. Take one slow breath in and let it out without rushing. And let's begin. The universe, when we talk about it at its largest scales, is not simply a sea of stars and galaxies scattered evenly through space. It has texture. It has structure. Some regions are dense with clusters of galaxies, tightly packed and blazing with light. Other regions are populated more modestly, with loose groups and filaments, chains of galaxies stretched between denser nodes. And then there are the voids, places where galaxies are absent or nearly so, where the usual richness of the cosmos simply does not exist, where, if you could travel there, the sky around you would be almost completely dark. Tonight, we are going to spend time with the largest of these voids that we have found so far. And as we move through it, we will ask not just how big it is, but what it means that such a place exists, why the universe creates emptiness on such a scale, what it feels like to sit with the idea of a region of space that is, by some measures, nearly 1 billion light years across, and what the existence of that emptiness tells us about the nature of everything else. This is a journey not into brightness, but into the space between the lights, a place that is defined not by what it contains, but by what it lacks. And in exploring that absence, we may find something unexpected, a kind of beauty, a kind of quiet, a kind of meaning that reveals itself only when you are willing to sit with emptiness long enough for it to speak. When we imagine the universe, our minds naturally reach for what is visible, the glow of galaxies, the bright threads of filaments, the dense knots of clusters where thousands of galaxies crowd together in a gravitational family. These are the landmarks of the cosmic map, the features that draw the eye and give the universe its structure. But there is another side to that map, the spaces between the landmarks, the regions where the density of matter drops so low that the usual rules of cosmic architecture seem not to apply. These are the cosmic voids, and they are far more than mere absences. To understand what a void is, it helps to think first about how matter is arranged in the universe at large. Imagine pulling back from Earth, far past the solar system, far past the Milky Way, far enough that individual galaxies become tiny points of light. Keep pulling back until you can see clusters and superclusters. Keep going until you can see the structure that underlies it all. What you would find is something that astronomers call the cosmic web, a vast network of filaments, sheets, and nodes made of dark matter and ordinary matter, with galaxies gathered along the strands, like droplets of dew on a spider's web. The cosmic web is one of the most astonishing features of the universe. It is not random. It emerged from the earliest moments of cosmic history, from tiny fluctuations in the density of matter shortly after the Big Bang. Where matter was slightly denser, gravity pulled more matter in. The dense regions grew denser. Between them, matter was drawn away, leaving regions increasingly empty. Over billions of years, this process sculpted the web, pulling matter into filaments and walls, concentrating it into clusters, and leaving between these structures the great empty regions we call voids. A void, in this sense, is not merely an empty patch of sky. It is a region of space where the average density of matter is significantly lower than the cosmic average. Not zero, exactly. There may still be scattered galaxies within a void, and thin diffuse gas and dark matter in smaller quantities than elsewhere. But compared to the filaments and walls that border the void, the interior is dramatically underdense. The contrast between a void and the surrounding cosmic web is something like the contrast between a desert and a rainforest. The desert is not completely barren. There is life, there is sand, there is rock. But the density of life and water is so low compared to the forest that the two environments feel like entirely different worlds. The question of how big voids can get is one that has fascinated astronomers since they first began mapping the large-scale structure of the universe. In the early days of galaxy surveys, in the 1970s and 1980s, astronomers expected to find matter spread more or less evenly through space, with only modest variations in density. What they actually found was startling. Matter was clumped together in filaments and walls, and between those structures were enormous empty regions that no one had quite anticipated. The voids were not just small gaps. They were vast architectural features, as fundamental to the structure of the universe as the filaments and clusters that bounded them. The largest voids known to us stretch across hundreds of millions of light years. To cross the biggest of them at the speed of light, the fastest possible speed, would take hundreds of millions of years. And yet, these are not the exception. They are the rule. The universe is, in a sense, mostly void. If you could map all of the observable universe and shade in only the truly empty regions, you would find that voids occupy the majority of space. The galaxies and filaments we tend to think of as defining the cosmos are, in terms of volume, the minority. The universe's default state, on large scales, is emptiness. This can be a difficult thing to absorb. We are embedded in a galaxy. We are surrounded by stars. Our sky, even on the clearest night, is full of light. It is natural to think of the universe as a place full of things. But on its largest scales, the universe is mostly nothing, or rather, mostly something so thin and sparse that it is close enough to nothing to feel that way. The voids are not the exceptions on the cosmic map. They are the dominant feature, and the largest of them, the one we are going to spend time with tonight, is the Boötes Void. Before we move deeper into the Boötes Void specifically, it is worth pausing to think about what it takes to discover something so large. You might expect that finding a vast empty region of space would be straightforward. After all, emptiness should be easier to see than fullness. But in practice, discovering voids requires something counterintuitive. It requires mapping what is there in order to identify what is not. The history of cosmic cartography is a history of increasing ambition. For most of human history, the universe, as far as anyone could map it, was the night sky, a dome of stars overhead, fixed in their patterns, beautiful and mysterious. Even after Copernicus and Galileo and Newton transformed our understanding of the solar system, the stars themselves remained largely unmeasured. Their distances were unknown. Their arrangement in 3 dimensions was a matter of speculation. It was only in the 19th century that parallax measurements began to give us distances to the nearest stars, and the true 3-dimensional architecture of the stellar neighborhood began to emerge. By the early 20th century, the debate was still raging about whether the Milky Way was the whole universe or just one galaxy among many. It took Edwin Hubble's measurements of Cepheid variables in the Andromeda Nebula to settle the matter, establishing that other galaxies existed far beyond our own. Once it was clear that galaxies were the building blocks of the universe, the next challenge was to map them in 3 dimensions. A photograph of the sky gives positions on the sky, 2 dimensions, right ascension and declination, but not depth. To know how far away a galaxy is, you need its distance, and for most galaxies, that means measuring its redshift. As the universe expands, galaxies move away from us, and their light is stretched, shifted toward the red end of the spectrum. The greater the redshift, the greater the distance. By measuring the redshifts of large numbers of galaxies and combining that with their positions on the sky, astronomers can build 3-dimensional maps of the universe. In the late 1970s and early 1980s, astronomers began conducting large redshift surveys, measuring the distances to hundreds and then thousands of galaxies. These surveys were painstaking. Each galaxy required time at a telescope, careful measurement, careful data reduction. But as the catalogs grew, the large-scale structure of the universe began to emerge, and what emerged was astonishing. In 1981, a team of astronomers was studying a region of sky in the direction of the constellation Boötes. They were mapping galaxies in that part of the sky, building up a picture of the 3-dimensional distribution of matter. What they found when they plotted the data was something they had not expected, a region spanning tens of millions of light years across, where, essentially, there were no galaxies. The galaxies they were mapping in that direction were clustered along the boundaries of a great sphere of emptiness. The interior of that sphere appeared almost entirely devoid of galaxies. It was as though someone had scooped a vast bubble out of the universe. The astronomers called it the Boötes Void, naming it for the constellation in whose direction it lies from Earth. When they published their findings, the scale of the void shocked the astronomical community. It was so large that it seemed, to many, to challenge the models of how cosmic structure had formed. Nothing in the then current understanding of the universe easily explained how such a large, empty region could exist. In the years and decades since that discovery, astronomers have refined their measurements of the Boötes Void. They have mapped it in greater detail, found its boundaries more precisely, and debated its true extent. And the more they have looked, the more extraordinary it has appeared. Modern estimates place the Boötes Void at roughly 330 million light-years across in diameter. Some analyses suggest it may be even larger. Either way, it is one of the largest single structures, or perhaps more accurately, one of the largest single absences that astronomers have ever identified in the observable universe. To cross it at the speed of light would take over 300 million years.
At the speed of our fastest spacecraft, it would take many times the current age of the universe. It is not just large, it is an almost incomprehensible emptiness sitting there.
In the darkness of space, defined entirely by the absence of what surrounds it. The name Boötes comes from the constellation in whose direction we see the void from Earth. The constellation Boötes is one of the larger constellations in the northern hemisphere's night sky. Its name comes from the ancient Greek word for herdsman or plowman, and it is dominated by the bright star Arcturus, one of the brightest stars visible from Earth, a warm orange giant about 37 light years away. When you look toward Boötes on a clear night, the light of Arcturus and the surrounding stars is coming from within our own galaxy, from our own cosmic neighborhood. But the void that bears the constellation's name lies vastly farther away, not 37 light years distant, but hundreds of millions of light years, in a part of the universe so remote that the galaxies there are beyond easy observation. It is worth sitting with that layering for a moment. When you look up at the night sky and see the constellation Boötes, you are looking at stars that are, by cosmic standards, immediately next door. The light from Arcturus left that star about 37 years ago. If you are in your 30s, that light began its journey before you were born. And yet, far beyond Arcturus, beyond all the stars you can see, beyond even the faint smudges of the nearest galaxies that a telescope might reveal, there is this enormous empty region of space bearing the same name as the constellation, but existing on an entirely different scale. This kind of layering is one of the things that makes astronomy simultaneously bewildering and beautiful. The night sky is not a flat backdrop. It is a deep, three-dimensional space, with distances stacked upon distances, each layer belonging to a different epoch and a different scale of structure. The stars we see with the naked eye are our immediate neighborhood. The galaxies, visible in a moderate telescope, are thousands to millions of light years away. The galaxy clusters, mapped in large surveys, are tens to hundreds of millions of light years distant, and the great voids and walls of the cosmic web stretch across hundreds of millions of light years, encoding the very large-scale structure of the universe. When you look toward Boötes, you are looking through all of those layers at once. The star Arcturus is in the foreground. Beyond it are countless other stars in the Milky Way. Beyond the Milky Way are other galaxies. And far, far beyond those, in the background of that particular direction of sky, lies the enormous emptiness of the Boötes Void. The fact that a void is named for a direction in the sky rather than a physical location is itself revealing. Voids do not have addresses in the way that planets or stars do. They do not have a bright center we can point to. They are defined by their surroundings, by the walls of galaxies that bound them. In a sense, naming a void after the constellation in whose direction we see it is honest. The void is not a thing with a location so much as an absence with a direction. But that absence is real. It is physically real. It is not a gap in our data or an artifact of incomplete observation. It is a genuine feature of the universe, a place where the rules that have concentrated matter into stars and galaxies and clusters have, for whatever reason, left an enormous volume of space nearly empty. Let's try to hold the size of the Boötes Void in our minds, even though doing so is genuinely difficult. We have said it is roughly 330 million light years across. Let's try to give that number some texture. A single light year is the distance that light, traveling at nearly 300,000 kilometers per second, covers in one full year. That is approximately 9.5 trillion kilometers. If you set off from Earth at the speed of our fastest spacecraft, the kind of velocity achieved by the Voyager probes after decades of travel, a single light year would still take tens of thousands of years to cross. Now multiply that by 330 million. That is how wide the Boötes Void is. If you could somehow travel at the speed of light and you entered the Boötes Void at one edge, the journey to the opposite wall would take you over 300 million years. Think about what has happened on Earth in 300 million years. 300 million years ago, the continents were arranged in a completely different configuration. Life on Earth had not yet produced dinosaurs. The first reptiles were only just beginning to appear. The forests of that era were full of giant insects. Everything that has happened in the history of the animal kingdom, in all of its diversity and complexity, the age of dinosaurs, the extinction event, the rise of mammals, the evolution of primates, the entire history of our species, would fit inside the time it would take to cross this void at the fastest possible speed. Another way to picture it, the Milky Way is roughly 100,000 light years across. The Boötes Void is about 3,300 times wider than our entire galaxy. If the Milky Way were shrunk to the size of a single coin, the Boötes Void at the same scale would be about 3 kilometers wide. Our galaxy, which already takes 100,000 years to cross at the speed of light, would be a tiny disk inside a space 3 kilometers in diameter. Or consider that the distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years. The Boötes Void is more than 130 times wider than that distance. You could fit the gap between the Milky Way and Andromeda into the Boötes Void more than 100 times and still have room to spare. These comparisons are not meant to overwhelm, but to gesture at something. The Boötes Void is not just a slightly larger than average empty region. It is a feature of the universe that operates at a different order of magnitude from the things we usually describe when we talk about space. It belongs to the very largest scale of cosmic structure, the scale at which the universe begins to look smooth and featureless in one direction, while in others it is crammed with walls and filaments of galaxies. It sits at the boundary between the structured cosmos and something that feels almost like nothing. And sitting at that boundary is where its mystery and its beauty both reside. The Boötes Void was not mapped all at once. Its discovery and characterization unfolded over years of careful observation, and that process is itself a story worth telling slowly. When the void was first identified in 1981, the evidence came from a relatively sparse survey of galaxies in that region of sky. The astronomers who found it, Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, were conducting what was called a pencil beam survey. Rather than mapping galaxies across the whole sky, they measured the distances to galaxies along a narrow line of sight, like taking core samples through the cosmic structure. When they plotted their measurements, they noticed a dramatic gap in the distribution of galaxies. In a region spanning hundreds of millions of light years in depth, the galaxies simply disappeared. The initial discovery showed that the region was strikingly empty, but the exact extent and shape of the void were not immediately clear. Subsequent observations filled in the picture. As more redshift surveys were conducted and more galaxies were mapped in and around the Boötes direction, the boundaries of the void became clearer. What emerged was a roughly spherical or slightly elongated, empty region, larger than anything astronomers had expected to find. When the result was first announced, the reaction in the astronomical community was a mixture of excitement and skepticism. Some wondered whether the void was really as empty as the data suggested, or whether the surveys had simply missed galaxies that were too faint to detect. This was a legitimate concern. The galaxies visible in a survey depend on how sensitive the telescopes are and how much time is spent looking. Faint galaxies, of which there are many more than bright ones, could easily be missed. Subsequent, more sensitive surveys addressed this concern. They found that while the Boötes Void does contain a small number of galaxies, particularly some that were discovered in the 1980s and 1990s, as technology improved, the interior remains dramatically underdense compared to the surrounding universe. The handful of galaxies found inside the void are not enough to change the fundamental character of the region. It is genuinely, substantially empty. One of the intriguing details to emerge from the follow-up surveys was the structure of the galaxies within the void. Most of the galaxies found inside the Boötes Void appear to be arranged, not randomly scattered through the interior, but gathered into small filaments and chains within the void itself. This might sound like a contradiction. If the void is supposed to be empty, why are there filaments inside it? The answer is that voids are not perfectly homogeneous. Even within a void, gravity is still at work. Matter that finds itself inside a void does not simply sit still. It is drawn outward toward the walls, where the density is higher and the gravitational pull is greater. This tends to evacuate the void further over time, drawing matter toward the edges. But some matter, caught in local gravitational arrangements, may cluster into small structures within the void, even as the larger scale flow evacuates the space around them. The galaxies found within the Boötes Void may represent remnants of this process. Small concentrations of matter that have not yet been swept out to the walls, or small structures that have grown within the void itself. In a sense, the interior of the Boötes Void is not simply empty. It is a region where the usual process of structure, formation, the gathering of matter into filaments and clusters, has proceeded so slowly and with so little material that the structures formed are tiny by cosmic standards. The void's interior is not the absence of all structure. It is a place where structure exists at a much smaller scale, in a much more diluted form. This is one of the things that makes voids fascinating as objects of study. They are not merely passive, empty spaces. They are active physical environments where matter behaves differently, where the gravitational landscape is shaped by the surrounding walls rather than by the local density. Void interiors are, in a sense, laboratories for studying how matter behaves in low-density environments. And the Boötes Void, as the largest known void, is the most extreme such laboratory we have found. To understand why the Boötes Void exists, we need to go back to the beginning. Not the beginning of the void itself, but the beginning of everything. In the first fraction of a second after the Big Bang, the universe was extraordinarily hot, extraordinarily dense, and extraordinarily uniform. The matter and energy were distributed almost perfectly evenly through space. But almost perfectly is not perfectly. There were tiny variations in density, fluctuations at the quantum level that, through the process of cosmic inflation, were stretched to macroscopic scales. These fluctuations were incredibly small, perhaps 1 part in 100,000, but they were there over the next hundreds of thousands of years. As the universe expanded and cooled, these fluctuations began to matter. In regions of slightly higher density, gravity pulled matter together a little more strongly. In regions of slightly lower density, matter was drawn away more readily. The fluctuations began to grow. By the time the universe was about 380,000 years old, it had cooled enough for electrons to combine with protons to form neutral hydrogen atoms. This moment, called recombination, freed the photons that had been bouncing around in the dense plasma, and they streamed away as the cosmic microwave background, the oldest light we can detect. At this moment, the fluctuations in density were still tiny, imprinted in the subtle temperature variations of the microwave background that we can measure today with extraordinary precision. From that point, gravity took over. Over billions of years, the slight overdensities grew into filaments, walls, and clusters. The slight underdensities grew into voids. The process was slow but relentless, driven by the mathematics of gravitational collapse and expansion. Matter fell toward overdense regions, accelerating as it fell, building up more mass, becoming more gravitationally dominant, and drawing in more matter still. Meanwhile, the underdense regions were depleted as matter flowed out of them toward the walls. This process, called gravitational instability, is the engine of cosmic structure formation. It is why the universe today has the web-like structure we observe. It is why galaxies exist at all, and why they are distributed in filaments and clusters, rather than spread uniformly through space. It is also why voids exist. A void is, in this picture, the natural consequence of the same process that created the filaments and clusters. Wherever the initial density fluctuation was sufficiently negative, wherever the density was slightly below average in that early universe, matter has flowed out over billions of years, leaving an expanding region of emptiness behind. The larger the initial underdensity, the larger and emptier the void that has grown from it. The Boötes Void on this picture grew from a region of slightly below average density in the early universe. Over the 13.8 billion years since the Big Bang, that region has expanded and emptied as matter flowed toward the surrounding walls. The fact that the void is so large suggests that the initial underdensity from which it grew was itself large, spanning a region of early space that, when expanded by cosmic growth, became the vast empty bubble we see today. But here is where the Boötes Void becomes genuinely puzzling. By most accounts, the standard model of cosmic structure, formation, does not easily predict that voids this large should exist. The fluctuations in the early universe, as measured by the cosmic microwave background, should not have been large enough to produce an underdensity that grows into a void as large as the Boötes Void. The universe's structure, on average, is well described by the standard model, but the Boötes Void sits at the edge of what that model comfortably explains. This does not mean the standard model is wrong, but it does mean that the Boötes Void is extraordinary, even within the context of a universe that is already full of extraordinary things. It is a statistical outlier, a feature that sits at the tail of the distribution of void sizes. Either the universe produced it through an unusually large fluctuation, which is possible but unlikely, or there is something about the local history of that region of space that we do not fully understand, or perhaps our measurements of its size or emptiness need further refinement. Astronomers continue to debate these possibilities, and the Boötes Void remains one of the most discussed large-scale structures in cosmology precisely because it challenges easy explanation. What would it be like to be inside the Boötes Void? This is a question that admits no practical answer because we will never go there. The distances involved are so vast that no form of travel could bring us there in any conceivable human time frame. But the imagination is not subject to the same constraints as our spacecraft. So let us take a moment and imagine it. You are inside the Boötes Void. Perhaps you are aboard a ship, or perhaps you are simply a consciousness suspended in space, an observer without a body. Around you, in every direction, is darkness. Not the darkness of a room with the lights off, where your eyes adjust and you begin to see shapes. Not the darkness of a moonless country night, where the Milky Way blazes overhead and thousands of stars are visible. No, this is a different kind of darkness, a deeper kind. In every direction, you look for the familiar signs of cosmic presence. You look for the glow of nearby stars, the faint smudge of a galaxy, the clustered brightness of a group, and you find almost nothing. In the direction of the Boötes Void's walls, far away on the boundary of the void, there might be the faintest suggestions of structure. The walls of the void, made of the filaments and sheets of galaxies that define the boundary, might be visible as extremely faint concentrations of light if your instruments were sensitive enough. But with the naked eye, or even with a modest telescope, the boundary would likely be invisible. You would simply see darkness in every direction, with only the most sensitive instruments able to detect that there is something far away, marking the edge of the emptiness you inhabit. The cosmic microwave background would still be present everywhere around you. That ancient glow, the afterglow of the Big Bang, permeates all of space equally. You could detect it with the right instruments. And dark matter, too, would still be present in small quantities. The void is not a perfect vacuum, but compared to the regions of space that surround the void, you would be in an environment of extraordinary sparseness. If you looked up at the sky from within the Boötes Void, what you saw would be profoundly different from what we see from Earth. On a clear, dark night in a remote location on Earth, you can see several thousand stars with the naked eye, all of them within our galaxy, all of them within a few thousand light years at most. Even from outside the Milky Way, looking back at it, you would see a faint spiral of light. But from the interior of the Boötes Void, the Milky Way itself would be invisible. The distance is too great, the light too faint. You would need a large telescope to see our galaxy at all. From the deep interior of the void, all galaxies would be remote. All stars would be beyond naked eye visibility. The sky would be a pure, deep darkness, broken only by the very faint smudges of the most distant and luminous objects, visible with powerful telescopes. It would be, in the truest sense, a dark sky, darker than any sky visible from within a galaxy, darker than the sky seen from the surface of the moon, or from deep space within our own cosmic neighborhood. There is something both profound and unsettling
about imagining this place. The universe, from our perspective on Earth, feels full. Even when we think about the vastness between galaxies, we are surrounded by the light of our galaxy's hundreds of billions of stars. We are embedded in a rich environment. The Boötes Void is the opposite of that. It is the universe stripped of its usual richness, reduced to its most fundamental and spare state. A place where the cosmos has undressed itself and shown you what it looks like when all the usual decoration is absent. And yet, even there, the universe is not nothing. The laws of physics still hold. Space still curves in response to mass. Even if that mass is tiny, dark energy still pushes the universe apart. The cosmic microwave background still fills every corner of space with its ancient warmth. The void is not absence in any absolute sense. It is the universe at its most dilute, its most empty, its most quiet, and quiet is not the same as nothing.
The galaxies that do exist within the Boötes Void, the handful that surveys have found in its interior, are worth thinking about for a moment, because they tell us something about what life is like in an extreme environment. When we talk about galaxies inside a void, the word inside is a relative one. A void is not a container with walls you can touch. It is a statistical region of lower than average density. A galaxy that happens to find itself in the interior of such a region is simply a galaxy that formed in a place where matter was sparser than average. The galaxies found within the Boötes Void tend to be different in subtle ways from galaxies found in denser regions of the universe. In denser regions, galaxies interact more frequently. They pass close to one another, their gravity disturbing each other's structure, triggering bursts of star formation, sometimes even merging. The richness of a cluster of galaxies is not just about numbers. It is about the dynamism of all those interactions. In the void, by contrast, the nearest galactic neighbor to any given galaxy is likely to be extremely far away. Interactions are rare. A galaxy sitting in the interior of the Boötes Void may have evolved in relative isolation for billions of years, undisturbed by the gravitational influence of nearby companions. This isolation is not necessarily a disadvantage, but it means that the galaxy's history is different. Its star formation has been driven more by internal processes than by the external triggers of interaction. Its structure may be more regular, less disturbed. Some observations suggest that galaxies and voids tend to be slightly bluer, indicating younger stellar populations, and to have somewhat higher rates of star formation than might be expected given their isolation. This is somewhat counterintuitive. You might think that a galaxy in a sparse environment, with less material flowing in from surrounding filaments, would form stars more slowly. And in some respects, that is true over the long run. But there are competing effects, and the precise interplay of isolation, gas availability, and dark matter halo properties makes void galaxies a genuinely interesting subject of study. What is perhaps most remarkable about the galaxies inside the Boötes Void is simply that they are there at all, in a region where the average density of matter is a tiny fraction of the cosmic average, where the nearest major concentration of galaxies is hundreds of millions of light years away. Matter has still managed to find ways to concentrate itself, to collapse into stars, to build galaxies. The drive toward structure, the tendency of matter to gather under its own gravity, is so fundamental that it persists even in the most extreme environments. Even in the emptiest place we know of, the universe cannot help but build things. This is, in some ways, one of the most remarkable facts about the cosmos. Structure formation is not fragile. It does not require special conditions or particularly rich environments. Given time, given gravity, and given even the slightest excess of matter over the cosmic average, the universe will build something. The galaxies inside the Boötes Void are testimony to the persistence of that process. Let's take a step back from the Boötes Void specifically and think about cosmic voids more generally, because the Boötes Void does not exist in isolation. It is the largest known member of a family of structures that, taken together, define a large part of the universe's volume. Voids of various sizes have been cataloged by astronomers over the past several decades. The smallest voids are tiny by cosmic standards, perhaps a few tens of millions of light years across. Others are intermediate in size, 100 or 200 million light years across. And then there is the large end of the distribution, the supervoids, of which the Boötes Void is the most famous example. The distribution of void sizes in the universe is not random. It follows patterns that reflect the underlying physics of structure formation. Smaller voids tend to be more numerous, while larger voids are rarer. This is analogous to the distribution of galaxy cluster sizes. Small clusters are common, while the most massive clusters are rare outliers. The Boötes Void's extraordinary size makes it, statistically speaking, a rare thing. Within a given void, something interesting happens over time. The void does not simply sit still, it grows. As matter flows outward from the interior toward the surrounding walls, the void expands, becoming both larger and emptier. Voids are not static features of the cosmic web. They are dynamic, evolving structures that grow throughout the history of the universe. There is also a tendency for smaller voids to merge into larger ones. Just as galaxies merge into larger galaxies over time, smaller voids that are adjacent to one another can merge as their walls dissolve and matter flows away. Over cosmic timescales, this merging process means that the large voids we see today, like the Boötes Void, may themselves be the result of the merging of multiple smaller voids over billions of years. This picture of void growth and merging is actually well captured in computer simulations of cosmic structure formation. When astronomers run simulations of the universe from shortly after the Big Bang to the present, they see the cosmic web develop in exactly the way observations suggest. Filaments grow, clusters form, and voids expand and merge. The Boötes Void, in this picture, is the grown-up result of a long process of evacuation and consolidation, a vast empty region that has been growing since the earliest times. But there is another void that deserves mention alongside the Boötes, one that has been the subject of intense discussion and some controversy. It is called the Eridanus Supervoid, and it is found in the direction of the constellation Eridanus. Unlike the Boötes Void, which was discovered through galaxy surveys, the Eridanus Supervoid was identified partly through its effects on the cosmic microwave background. In the microwave background, there is a region known as the cold spot, a patch of sky that is significantly colder than average. One candidate explanation for this cold spot is a vast underdense region, a supervoid through which the ancient microwave radiation has passed. When photons from the cosmic microwave background travel through a void, they experience a slight shift in energy. In the early universe, when dark energy was less dominant, a photon entering a void would be slightly blue shifted,
as it fell into the gravitational potential well of the void, and then slightly redshifted as it climbed back out. These effects canceled out, leaving no net signature. But as dark energy began to dominate, it changed the geometry of the voids over time. Photons passing through a void in the dark energy-dominated universe lose a slight amount of energy on balance because the void is expanding and the photon has to climb out of a deeper potential well than the one it fell into. This effect is called the integrated Sachs-Wolf effect, and it means that photons passing through voids should arrive slightly colder than average. The Eridanus Supervoid, if it is real and if it is large enough, could explain the cold spot through exactly this mechanism. Some analyses of galaxy surveys have found an underdensity in that region of sky consistent with a supervoid perhaps 200 to 300 million light-years across. Others have challenged this interpretation, finding the evidence less convincing or the void less dramatic than claimed. The debate continues. What makes the Eridanus case interesting in the context of our
discussion is that it illustrates how voids are not just architectural curiosities. They have measurable effects on the light passing through them. They leave their fingerprints on the oldest light in the universe. The voids of the cosmic web are not passive empty spaces. They interact with light, with dark energy, with the geometry of space-time in ways that we can detect and study. The Boötes Void, the Eridanus Supervoid, and the many other voids mapped by astronomers are active participants in the physics of the universe, not merely its absences. There is a philosophical dimension to the Boötes Void that is worth sitting with for a moment. The void is, by definition, defined by absence. It is known not by what it is, but by what it is not. It has no stars of its own, no center that glows, no landmark that marks it out in the sky. From within it, you would have no way of knowing you were in the void unless you had a map of the surrounding universe. The void announces itself only to those who are looking at it from outside. This is an unusual kind of existence. Most things in the universe are defined by their presence. A star is defined by its light, a galaxy by its structure, a cluster by its concentration of galaxies. But a void is defined purely by the contrast between its interior and its surroundings. It exists in a sense only in relation to the things that are not in it. There is something quietly profound in that. In our everyday lives, we tend to focus on presence over absence. We notice what is there rather than what is missing. We count the things in a room rather than the empty space between them. But the empty space is just as real as the things that occupy it. And in the universe, as we have seen, the empty space is actually the majority. The Boötes Void asks us to think differently about emptiness, not as the absence of something valuable, but as something in its own right. The void has its own physics. It has its own history. It has its own future. It is growing. It is evacuating itself further as matter flows toward its walls. In billions of years, it will be larger and emptier than it is today. It is not a passive absence. It is an active process. In this sense, the void is not the opposite of structure. It is structure of a different kind. The web of galaxies and the web of voids are not two separate things. They are two aspects of the same thing, the same underlying distribution of matter, shaped by the same gravitational physics. The filaments would not have their shape if the voids did not have theirs. The clusters would not be where they are if the voids had not evacuated the regions around them. The cosmic web is built equally from its density and its emptiness. They are inseparable partners in the architecture of the universe. If you find something calming in that thought, you are not alone. There is a quietness about voids that feels somehow appropriate at this hour. The universe contains within it enormous regions of almost perfect stillness, of darkness that has gone undisturbed for billions of years, of space that has been gently emptying itself since before Earth existed. The Boötes Void has been growing larger and quieter for most of the history of the universe, and it will continue to do so long after anything that currently exists has changed beyond recognition. There is a steadiness in that, a kind of deep cosmic patience that the void embodies simply by existing. When astronomers study the Boötes Void and structures like it, they use tools and techniques that are worth pausing to appreciate, because mapping something defined by absence requires a particular kind of ingenuity. The primary tool for mapping voids is the galaxy redshift survey. By measuring the distances to large numbers of galaxies through their redshifts, astronomers build three-dimensional maps of the universe. Where the galaxies cluster together, they identify filaments, walls, and clusters. Where the galaxies are sparse or absent, they identify voids. The quality of the void map depends on the quality of the galaxy survey. A sparse survey with few galaxies may miss smaller voids or mischaracterize larger ones. A dense survey with many galaxies gives a more accurate picture. Over the decades since the Boötes Void was discovered, galaxy surveys have grown enormously in scope and depth. The CFA Redshift survey of the 1970s and 1980s, which led to the discovery of the void, measured thousands of galaxies. The Sloan Digital Sky survey, which began in the late 1990s and continued for decades, measured redshifts for hundreds of millions of galaxies. The Dark Energy Spectroscopic Instrument, operating in the 2020s, aims to map tens of millions of galaxies with unprecedented precision. Each generation of survey has given a sharper and more detailed picture of the cosmic web, including its voids. Modern computational techniques have also transformed how voids are identified and characterized. Computer algorithms analyze the three-dimensional distribution of galaxies and identify voids automatically, measuring their size, shape, and depth. These algorithms can distinguish between a true supervoid like the Boötes Void and smaller, shallower underdensities. They can map the gradients of density from a void's empty core to its denser walls. They can track how voids connect to one another and to the larger cosmic web. Complementary observations in other wavelengths also add information. Radio telescopes can detect neutral hydrogen gas, which traces the large-scale distribution of matter even in regions where galaxies are sparse. X-ray observations can detect the hot gas that fills clusters and, in smaller quantities, threads through filaments. Gravitational lensing, the bending of light from distant objects by the gravity of matter in the foreground, can map the distribution of dark matter, which does not emit light, but is present even in voids. All of these tools together give a multi-layered picture of cosmic voids. They reveal that voids are not simple spherical bubbles. They have complex shapes, irregular boundaries, internal structure, and connections to the surrounding web. The Boötes Void itself is not a perfect sphere. It is somewhat irregular in shape, with some regions more evacuated than others, and its boundaries blend into the surrounding filaments in a gradual rather than sharp transition. There is also the question of what dark matter looks like inside a void. Since we cannot detect dark matter directly, only through its gravitational effects, mapping dark matter in a void is challenging. But simulations of cosmic structure formation give a consistent picture. Even in the most underdense voids, dark matter is present in quantities well above zero. The dark matter in a void is simply much less dense than the cosmic average, in proportions similar to the deficit of ordinary matter. The dark matter halo structure that surrounds each galaxy within the void is smaller and less massive than typical halos outside the void, reflecting the overall lower density of the environment. What all of this tells us is that the Boötes Void, for all its emptiness, is not a simple place. It is a region of the universe with its own physics, its own history, its own internal structure. It is large enough that studying it in detail requires combining many different observational techniques and computational tools, and it is strange enough that it continues to raise questions that astronomers have not fully answered. One of the questions that naturally arises when confronted with the Boötes Void is whether it is truly the largest structure of its kind, or whether there are even larger voids yet to be discovered. The honest answer is that we do not know. The observable universe is enormous, and even the most comprehensive galaxy surveys today have mapped only a fraction of it in the detail needed to identify and characterize all of the voids it contains. The surveys that exist have focused primarily on certain regions of sky and certain distance ranges. Voids in unmapped or poorly mapped regions of the universe would simply not appear in our catalogs. There is also the question of what it means to be the largest void. If we define a void strictly as a region significantly underdense relative to the cosmic average, with clear boundaries defined by surrounding walls or filaments, then the answer depends on where we draw the boundaries. The Boötes Void is large, but it sits within a larger context of underdense regions. Depending on how you define the void's edges, whether you draw them at one particular density threshold or another, the apparent size of the void can change significantly. Some analyses have suggested that the Boötes Void may be part of an even larger, underdense region, a kind of superstructure of voids that extends over an even greater volume. If multiple neighboring voids are taken together as a single underdense complex, the total extent of the structure could be larger than any individual void. But at some point, this becomes a matter of definition as much as observation. What we can say with some confidence is that the Boötes Void is among the very largest single voids identified in the observed universe with current data. Future surveys, with more galaxies mapped to greater distances with greater precision, may reveal larger voids, or may refine the boundaries of the Boötes Void and find it smaller or larger than current estimates suggest. The Sloan, Great Wall, the Hercules Corona Borealis, Great Wall, and other large structures discovered in recent decades have repeatedly surprised astronomers with their scale, pushing the boundaries of what the standard model of cosmology comfortably accommodates. It would not be surprising if future surveys discovered voids even larger than the Boötes Void. The universe is under no obligation to fit neatly within our theoretical expectations. There is something humbling and exciting in that uncertainty. The cosmic map is still being drawn. The largest structures in the universe are still being identified, characterized, and debated. Every new survey brings the possibility of discovering something that changes our picture of how matter is distributed through space. The Boötes Void was a surprise when it was found. Future discoveries may be equally surprising. Let's think for a moment about the future of the Boötes Void, because voids, like everything else in the universe, do not stand still. On the timescale of billions of years, the Boötes Void will continue to grow. Matter on its boundaries is still flowing outward, drawn by the gravitational influence of the surrounding filaments and walls. As the interior empties further, the void expands. The galaxies currently within the void, the sparse handful that surveys have found inside, are slowly being evacuated toward the walls, drawn by the same gravitational currents that have been flowing since the void began to form. Dark energy is also playing a role in the future of the Boötes Void. As dark energy drives the accelerating expansion of the universe, it affects the dynamics of voids in a subtle but important way. In a universe dominated by dark energy, the expansion of space becomes so rapid that even the gravitational pull of the surrounding filaments and walls is eventually overwhelmed. On very long timescales, trillions of years into the future, the accelerating expansion will stretch the distances between all objects beyond the gravitational reach that currently holds them together. In this far future, even the walls that currently define the Boötes Void will dissolve. The filaments of galaxies that mark its boundaries will be stretched apart by dark energy. The clusters that anchor those filaments will themselves be drawn apart if dark energy continues to accelerate. The void will grow, not just because matter is flowing out of it, but because the entire cosmic web will eventually be stretched thin by the relentless push of dark energy. In the very far future, some models suggest that the universe's large-scale structure, the cosmic web, with its filaments and voids, will fade away entirely, as expansion carries all structures beyond their mutual gravitational reach. In that scenario, the distinction between void and filament, between the Boötes Void and the walls that surround it, will become meaningless. The universe will become, on its largest scales, a vast and featureless expanse of isolated galaxies, then isolated stars, then isolated particles, growing colder and more diffuse without end. The Boötes Void, in that far future, will simply be a piece of a larger emptiness. The structure that currently defines it, the contrast between its interior and the surrounding walls, will dissolve. The void will no longer be a void in any meaningful sense, because everything around it will have become equally void. But that is a very long time away. In the present, the Boötes Void is a genuine feature of the cosmos, with clear boundaries, a distinct history, and an ongoing process of growth. It will be recognizable as a void for billions of years to come. There is something both sobering and strangely comforting in thinking about the long-term future of the void. The universe is not static. It is moving, changing, evolving on timescales so vast that our entire civilization is not even a blink. The Boötes Void that exists today is one frame in a long film, a film that began with the quantum fluctuations of the early universe and will end, if cosmological models are correct, in a cold and empty darkness of unimaginable scale. The void is not a final state. It is a phase, a moment in the ongoing story of matter and space and gravity. The Boötes Void raises questions not just about cosmology, but about our place in the universe, and not in the abstract sense of wondering whether we matter. Something more specific, more physical, something about where, in the cosmic web, we happen to live. We live in the Milky Way. which is part of the local group, which is part of the Virgo supercluster, which is part of the larger Laniakea supercluster. Our cosmic address is embedded in the overdense part of the universe. We live on a filament in a relatively rich region of the cosmic web, surrounded by other galaxies, other groups, other clusters. We are not in a void. This matters because the physics of our cosmic environment shapes the kind of universe we can observe. Living in a galaxy within a cluster of galaxies, within a supercluster, means we are surrounded by light. Our night sky shows hundreds of billions of stars in our own galaxy, and with a telescope, we can see thousands of other galaxies within reach. The richness of our local environment is the reason astronomy as a science has been possible. There has been enough matter nearby to give us things to observe, measure, and understand. If our solar system had formed inside a void like the Boötes Void, the observable universe would be a very different place. Our galaxy, if it formed at all in such a sparse environment, might be more isolated. The sky, seen through a telescope from a planet within the void, would show far fewer galaxies at close range. The material available for planetary formation might be different. The history of star formation in our region would have been different, which would have meant a different history of the heavy elements needed for planets and life. It is not entirely clear whether life of the kind we know would have been possible inside the Boötes Void. The first requirement for life as we understand it is a star like our sun. Stars like our sun require not just hydrogen and helium, but heavier elements, carbon, oxygen, nitrogen, iron, and others. These heavier elements are made inside stars and dispersed through space by supernova. They are then incorporated into subsequent generations of stars and their planetary systems. In a void environment where star formation proceeds more slowly and less efficiently over cosmic time, the enrichment of the interstellar medium with heavy elements might be delayed. The void environment might produce fewer supernovae per unit volume, per unit time, meaning fewer heavy elements scattered into space, meaning fewer of the raw materials needed for rocky planets and complex chemistry. Life inside the Boötes Void, if it exists, may have had a harder road to travel in terms of the raw material available. Of course, this is speculative. We do not know enough about the galaxies inside the Boötes Void, nor enough about the minimum conditions for life to say with confidence whether life could or could not arise there. But it is worth reflecting on how deeply our cosmic address shapes the universe we experience. We did not choose to live in the overdense part of the cosmic web. We are here because the physics of our region of the universe was such that matter concentrated, stars formed, heavy elements were made, a solar system arose, a planet formed in the right place, and chemistry proceeded for billions of years in the right direction. All of that was made possible, in part, by the fact that we live in a rich, dense region of the universe, rather than inside a vast cosmic void. The existence of the Boötes Void is a reminder that the universe is not uniformly hospitable. It has places where the conditions for complex structure, for stars and planets and perhaps life, are favorable, and places where they are not. We are fortunate to inhabit one of the former. The discovery of the Boötes Void had an effect on cosmology that went beyond the immediate excitement of finding a large structure. It contributed to a growing realization through the 1980s and beyond that the universe on its largest scales is profoundly structured in ways that early theoretical models had not fully anticipated. Before the large Redshift surveys of the 1980s, many cosmologists had assumed that the universe on scales larger than galaxy clusters would be relatively smooth, with only modest variations in the density of matter. The discovery of the Boötes Void, followed by the mapping of the Great Wall, a sheet of galaxies stretching hundreds of millions of light years, and other large-scale structures, showed that this assumption was wrong. The universe has significant structure on scales of hundreds of millions of light years, and the distribution of matter is far from uniform even on those enormous scales. This revelation had consequences for theoretical cosmology. Models of the universe had to accommodate not just the formation of galaxies and clusters, but the formation of the large-scale web itself, including the voids. This pushed theorists to refine their models of how dark matter behaves, how inflation shaped the initial fluctuations, and how structure has grown over cosmic time. The discovery also contributed to the development of observational cosmology as a discipline. Before the large surveys of the 1980s, cosmology was largely a theoretical enterprise, constrained by relatively sparse observational data. The surveys that revealed the cosmic web transformed cosmology into a richly data-driven science. The Boötes Void was one of the early results that demonstrated how much there was to learn from systematic mapping of the three-dimensional universe. In subsequent decades, the program of mapping the cosmic web has continued to expand. The Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, the VIMOS Public Extragalactic Redshift Survey, and many others have built progressively more detailed three-dimensional maps of the universe. These maps have confirmed and refined the picture, first glimpsed in the early 1980s, a universe structured into a web of filaments, walls, clusters, and voids, with the voids occupying most of the volume. The Boötes Void sits within this larger context as an important landmark, not just because it is the largest known void, but because it is one of the structures that first demonstrated, concretely and unmistakably, that the universe's architecture is far more complex and structured than had been imagined. It is a place that has, in a quiet and understated way, shaped our understanding of the cosmos. There is one more dimension to the Boötes Void that is worth exploring before we begin to draw our reflections together. It is the question of what the void tells us about the nature of dark energy. Dark energy, the mysterious component of the universe responsible for the accelerating expansion of space, makes up roughly 68% of the total energy content of the universe. It was discovered in 1998 through observations of distant supernovae that showed the universe was not just expanding, but expanding at an increasing rate. Since then, dark energy has been one of the great unsolved problems of physics. We know it exists because of its effects. We do not know what it is. Voids, and particularly large voids like the Boötes Void, offer a way to study dark energy that is complementary to other methods. The shape, size, and internal structure of voids are sensitive to the properties of dark energy. Different models of dark energy predict slightly different patterns of void formation and growth. By measuring voids carefully, particularly their clustering properties and the way their interiors look in cross-correlation with the cosmic microwave background, astronomers can put constraints on the nature of dark energy. The integrated Sachs-Wolf effect, which we mentioned earlier in the context of the Eridanus Supervoid, is one tool for this. When the cosmic microwave background photons pass through a void, they experience a slight temperature change. The magnitude of this temperature change depends on the properties of dark energy. By measuring the temperature of the microwave background in the directions of known large voids and comparing it to the average temperature, astronomers can extract information about dark energy. Large voids, like the Boötes Void, are particularly useful for this because the signal from the Sachs-Wolf effect is larger for larger voids. A supervoid hundreds of millions of light years across, if its density profile is well characterized, produces a measurable imprint on the microwave background. This makes supervoids valuable cosmological probes, tools for learning about the fundamental physics of the universe. The Boötes Void has been used in exactly this way. Studies have looked for the microwave background signal from the void direction and compared it to theoretical predictions. The results have generally been consistent with the standard model of dark energy. But the precision of these measurements continues to improve as both microwave background data and galaxy surveys improve. Future observations may be able to use the Boötes Void and similar structures to distinguish between different models of dark energy, potentially shedding light on one of the deepest mysteries in physics. This is a remarkable thing to contemplate. An enormous, empty region of space, defined by the absence of galaxies, turns out to be a tool for understanding the invisible energy that permeates all of space. The void is not just an absence, it is a measurement device. By studying what is not there, we learn something about the nature of the energy that drives the universe's expansion. Emptiness becomes a form of data. The Boötes Void and the cosmic web it belongs to raise questions about whether the universe we can observe is representative of the universe as a whole. This question is deeper than it might first appear. The observable universe is the region of space from which light has had time to reach us in the 13.8 billion years since the Big Bang. It extends about 46 billion light years in every direction. Within this bubble, we can observe galaxies, map the cosmic web, and study the large-scale structure. But the universe almost certainly extends far beyond our observable bubble, and we have no direct way to see it. This raises the question of whether the cosmic structures we observe, including the Boötes Void, are typical of what exists throughout the universe as a whole, or whether they are, in some sense, special or unusual. The standard cosmological model, which is supported by many lines of evidence, predicts that, on scales large enough, the universe is homogeneous, meaning that on average it looks the same in every direction and every location. This is called the cosmological principle. The cosmic web, with its filaments and voids, is consistent with the cosmological principle on scales where the statistical properties of the web are the same everywhere. A region of the universe far from our observable bubble should, on average, have the same density of filaments, clusters, and voids as our own region. The Boötes Void is not a violation of homogeneity in a statistical sense. It is a fluctuation, a region that is below average density by a large amount, but it is a fluctuation within a universe that is statistically uniform. However, there is a subtlety here. The cosmological principle says that the universe is homogeneous, on average, on large scales. On smaller scales, there are clearly large variations in density. The question is, what scale is large enough for the universe to appear smooth? Some of the largest structures discovered in recent years, the Hercules Corona Borealis Great Wall and similar features seem to be approaching or exceeding the scale at which the universe is supposed to look uniform, according to the standard model. If structures exist that are significantly larger than the scale of homogeneity predicted by the model, that would be a genuine challenge to the standard cosmological model. The Boötes Void is large, but it falls within the range of structures that the standard model can accommodate, if uncomfortably. As surveys map larger and larger volumes of the universe, these questions will be tested with greater precision. If voids or walls are found that are clearly larger than the model predicts, it would force a revision of our understanding of the early universe and of the processes that shaped its large-scale structure. This is one of the ways in which cosmic voids are not just curiosities. They are tests of fundamental cosmological theory. Every time we map a large void or a large wall, we are checking whether our models of the universe are correct on those scales. The Boötes Void has been one of the more challenging structures for the standard model to absorb. Future discoveries may be more challenging still. There is a certain meditative quality to thinking about the Boötes Void that becomes more apparent the longer you sit with it. It is, after all, a place where essentially nothing has happened for a very long time. A place where matter has been slowly and quietly flowing away since the earliest epochs of cosmic history, leaving behind an expanding emptiness that has known no supernova, no galaxy mergers, no clusters forming, no great events of the kind that define the rich inner life of galaxy filaments and walls. In the interior of the Boötes Void, there's a kind of patience that is difficult to find elsewhere in the universe. The universe is generally a place of great violence and great change on astronomical scales. Stars explode, galaxies collide, black holes devour surrounding matter and release enormous jets of energy. The cosmos is, despite its appearance from Earth, a place of constant upheaval. The Boötes Void, by contrast, is one of the quietest places in the observable universe. Not quiet in the sense of silence, which has no meaning in the vacuum of space, but quiet in the sense of low activity. In the interior of the void, over the course of billions of years, the most notable events have been the slow drift of matter outward toward the walls and the gradual growth of the void itself. There are no supernova lighting the interior, no cluster mergers sending out shockwaves of gas and radiation, no active galactic nuclei pouring energy into the surrounding medium, just the quiet, slow expansion of emptiness. This is not nothing. It is a kind of existence, a way of being in the universe that is different from the turbulent, energetic existence of matter in a galaxy cluster. The void exists. It has its own physics. It grows and changes, but it does so quietly, on timescales that dwarf even the long timescales of galaxy evolution. In a universe where everything seems to be happening at once, the void is the place where time moves differently, where change is so slow that billions of years feel like a moment. There is something about this slowness, this quietness, that feels restful, not because rest is the void's purpose. The void has no purpose. It is simply a consequence of physics. But the effect on the imagination is one of stillness, of a place that has been undisturbed for longer than continents have existed on Earth. A place where, if you could be there, the main thing you would experience is the gentle hum of the universe's background radiation and the absolute darkness of a sky, almost entirely empty
of the usual sources of light. For those of us who live in a world that rarely goes quiet, that image can be genuinely calming, not because we want the void for ourselves, but because knowing that it exists, knowing that the universe contains within it a place of such extraordinary stillness, is itself a kind of comfort. Let's draw some threads together now and think about what the Boötes Void tells us and what it leaves unanswered. It tells us that the universe's large-scale structure is not uniform. That matter has been gathered over billions of years into filaments and walls by gravity, leaving behind enormous regions of emptiness. That the void is not an accident or an error, but a fundamental feature of how the universe organizes itself. It tells us that emptiness is not nothing. The void has its own physics, its own history, its own dynamics. It contains a small number of galaxies and thin, diffuse gas. It interacts with the microwave background radiation. It probes the nature of dark energy. It is a participant in the physics of the universe, not a bystander. It tells us that our models of cosmic structure formation, while powerful and successful in many ways, are still being tested by the universe. The Boötes Void sits at the edge of what the standard model comfortably predicts. It is a challenge, a puzzle, a reminder that the universe is under no obligation to conform to our expectations. It tells us something about our own place in the cosmos. We live in a rich, dense region of the universe, embedded in a galaxy, within a cluster, within a supercluster. That richness is not a coincidence from our perspective. It is the condition that made us possible. The Boötes Void, by contrast, is a place where the conditions for complex structure and perhaps life are far less favorable, and it leaves unanswered the question of whether it is truly the largest void in the universe, or merely the largest one we have found so far. Future surveys may reveal larger voids. Future analysis may refine the Boötes Void's true extent. The cosmic map is still being completed, and the universe has not yet shown us everything it contains. What the Boötes Void does not tell us is anything about purpose or meaning in any teleological sense. The void did not form to teach us something. It did not form for any reason at all. It formed because of physics, because of the laws of gravity and expansion, and dark energy operating on the initial conditions set by the Big Bang. Its existence is a fact of the universe, not a message. But the meaning we make from it, the way it shapes our understanding of the cosmos and our place within it, that is entirely ours to construct, and the construction is worthwhile. To know about the Boötes Void is to know something true and important about the universe. To sit with the knowledge of its size, its emptiness, its age, its quiet persistence, is to enlarge our sense of what the cosmos contains and how extraordinary it is to be a small, conscious part of it. There is one more thought worth sitting with before we allow the Boötes Void to recede into the background of our awareness. The void is 330 million light-years across. The light we observe from its walls and from the sparse galaxies within it has been traveling toward us for hundreds of millions of years. The void we see is not the void as it is now, but the void as it was when that light began its journey. The universe has continued to change in the time it took the light to reach us. The void has continued to grow. The galaxies within it have continued their slow drift toward the walls. Everything we observe is already history. This is true of everything we see in the universe. Every star,
Every galaxy, every nebula, every cosmic structure is seen not as it is, but as it was. The night sky is a layered record of the past, with each distance corresponding to a different era of cosmic history. The Boötes Void, seen in the light reaching us today, shows us what that region of space looked like hundreds of millions of years ago. The present state of the void is inaccessible to us, separated from us not just by distance, but by time. And yet, in a sense, this does not diminish the void. It makes it richer. The image we have of the Boötes Void is not just a snapshot of a place. It is a snapshot of a moment in cosmic history. It shows us the universe as it was, part of the long record of how things have changed and grown and evolved since the Big Bang. Every observation we make is an act of archaeology as much as astronomy. We are reading the past written in light. The Boötes Void, then, is not just the largest known empty region of space. It is also a window onto a specific moment in the universe's past, a moment when a vast underdense region had been growing for billions of years and had reached the size we see, a moment preserved in light, sent toward us across the universe, arriving at our telescopes after a journey of hundreds of millions of years, and telling us something true about a place we will never visit, and a moment we can never return to. That is not nothing. In fact, it is remarkable that photons of light, the quietest and most fundamental of messengers, can carry across hundreds of millions of light years the information encoded in the distribution of matter, and that we, small beings on a small planet, can read those messages and reconstruct from them the architecture of the universe's emptiest place. The Boötes Void exists. It has existed, in growing form, for most of the universe's history. It will continue to exist, growing larger and quieter, for billions of years to come. And we, in our brief moment of awareness, have found it, named it, measured it, and tried to understand it. That is our contribution to the universe's long story. Not a large contribution in physical terms, but perhaps meaningful in the only way that meaning ever happens, which is in the act of one part of the universe becoming aware of another. As we bring this slow exploration to a close, let's return to the beginning, to the simple image of you, wherever you are right now, at the end of a day, in a room with dimming light, or perhaps outside under a sky that may or may not show stars. The universe around you tonight is the same universe that contains the Boötes Void. The atoms in your body were made in stars that belong to the same cosmic web that has produced those enormous walls of galaxies and those vast empty spaces between them. You are connected to all of it, not metaphorically, but physically, through the shared matter and energy and laws of physics that tie every corner of the observable universe to every other. The Boötes Void is not separate from you. It is part of the same universe you inhabit. The same expansion that is slowly growing the void is also growing the distances between our galaxy and others. The same dark energy that will eventually dissolve the cosmic web is the same dark energy that fills the space in your room, in the air around you, in the vacuum between atoms. The void and you are made of different densities of the same stuff, shaped by the same forces, existing at the same moment in cosmic history. And yet, the void is extraordinary because of how different it is from where you are. You are in a place of extraordinary richness by cosmic standards. You are on a planet with water and air and light, orbiting a star, within a galaxy teeming with hundreds of billions of other stars, in a part of the cosmic web that is overdense with matter and life and complexity. The void is the opposite of all that. It is the universe at its most spare, its most stripped down, its most quiet. To know about the Boötes Void is to know that the universe contains both of these things, the richness and the emptiness, the crowded filaments and the vast expanses of almost nothing, the bright clusters and the dark interior of the largest known void. It is all part of the same universe, the same cosmic story, the same ongoing process of matter organizing itself under the influence of gravity and dark energy, and the initial conditions set by the Big Bang. There is room for both in the universe, room for the complexity of life, and room for the simplicity of the void, room for the bustling of galaxies in a cluster, and room for the quiet of an almost empty bubble of space, hundreds of millions of light years across. The universe is large enough to contain all of these things simultaneously, and it does. As you let your body settle into rest, it is worth carrying that thought with you. The universe is large enough to contain everything, including the stillness of its largest voids, including the small, temporary, extraordinary fact of you, conscious and wondering at this particular moment in cosmic history. The void is out there, growing quietly, sending its ancient light toward us across hundreds of millions of light years. We have noticed it. We have measured it as best we can. We have given it a name. And then we have gone on with our lives, as one does, in the knowledge that the universe is stranger and larger and quieter and more beautiful than any single moment of attention can fully hold. That is enough, more than enough. The Boötes Void will be there tomorrow, and the universe will always be waiting. If tonight's journey through the emptiest place we know of left something to settle in you, something quiet and wide, you might find it worth returning here again. There is always another question at the edge of what we know, always another dark region of the universe to explore at the pace of a slow breath. If you would like to drift through more of these explorations, you can follow along or share this moment with someone who might need a quieter kind of company tonight. For now, let your breathing slow. Let the images of that vast darkness settle in your mind without needing to hold all of it at once. The Boötes Void is 330 million light years across. You are here. The distance between those two facts is the measure of the universe's generosity. It contains both, without contradiction, without effort, without end. Good night. When we think about the Boötes Void in the context of everything else we know about the universe, there is a question that keeps surfacing quietly in the background. Why here? Why did this particular region of space, in the direction of Boötes from our vantage point, develop into the largest known void? What combination of initial conditions and subsequent physics produced an empty region this large in this particular part of the cosmos? The honest answer is that we do not fully know, but we can lay out what we do know and let that picture build slowly. Go back, once more, to the very early universe. In the first fraction of a second, the universe was filled with a hot, dense plasma, a soup of quarks, electrons, and photons and neutrinos, all interacting furiously. The density was extraordinarily high, and the universe was expanding rapidly. But within this plasma, at the quantum level, there were fluctuations. The laws of quantum mechanics ensure that physical quantities are never perfectly definite, and in the early universe, these quantum variations in energy density were everywhere. These fluctuations are not just a technical detail. They are the seed of everything. Without them, the universe would have expanded uniformly and forever remained a smooth, featureless sea of hydrogen and helium. There would be no stars, no galaxies, no cosmic web, no voids, and no us. The fluctuations are where structure comes from. During a period called inflation, which is thought to have occurred in the first unimaginably brief moment of cosmic history, the universe expanded enormously in a very short time. This expansion stretched those tiny quantum fluctuations to macroscopic scales, imprinting them across space as variations in energy density. When inflation ended and the universe settled into its subsequent, more gradual expansion, those fluctuations were encoded in the distribution of matter and energy across the cosmos. The cosmic microwave background, which we can measure today with extraordinary precision, shows us these fluctuations as they were 380,000 years after the Big Bang. The temperature variations in the microwave background, tiny as they are, correspond to the fluctuations in density that inflation stretched to cosmic scales. They are a map of the seeds of all cosmic structure. The Boötes Void, like every other feature of the large-scale structure, grew from these seeds. In the region of the early universe that corresponds to the location of the Boötes Void, today, the initial density fluctuation was negative, meaning the density there was slightly below the cosmic average. As the universe expanded, gravity pulled matter away from that underdense region toward the surrounding overdensities. The underdense region grew larger and emptier over time. What began as a tiny negative fluctuation became, after 13.8 billion years of gravitational dynamics, the vast empty bubble we observe today. This much is consistent with our understanding of cosmic structure formation. The specific size and depth of the Boötes Void, however, is where questions remain. The standard model of cosmology, based on the cold, dark matter paradigm, with a cosmological constant representing dark energy, predicts the statistical distribution of voids in the universe. Most voids fall within the range the model predicts, but the Boötes Void is large enough that it sits toward the extreme end of the predicted distribution, or perhaps slightly beyond it. This does not necessarily mean the model is wrong. The model makes statistical predictions, and statistics allow for rare events. A void as large as the Boötes Void could be a statistical fluctuation within an otherwise well-described universe, a rare outcome that the model does not rule out, but that it does not predict to be common. The question is whether the Boötes Void is the kind of outlier the standard model can accommodate as a rare event, or whether it is so extreme that it challenges the model in a more fundamental way. Astronomers have not reached a consensus on this. Some analyses conclude that the Boötes Void is within the expected range of the standard model, if toward the tail of the distribution. Others argue that it is large enough to create genuine tension with the model. The debate continues as surveys improve, and as our computational simulations of cosmic structure formation become more sophisticated. What is certain is that the Boötes Void is not easily dismissed as typical. It is, by any measure, an extraordinary feature of the universe. The question of exactly how extraordinary it is and what that implies for cosmology is one that active research is still trying to answer. To appreciate the full strangeness of the Boötes Void, it helps to compare it not just to other cosmic structures, but to our most familiar frame of reference, the human scale. The Boötes Void is approximately 330 million light years across. 1 light year is about 9.5 trillion kilometers. Multiplied by 330 million, you get a number with so many zeros that writing it out in ordinary notation would produce something incomprehensible. In scientific notation, the diameter of the Boötes Void is approximately 3.1 times 10 to the power of 24 kilometers. That is 3.1 followed by 24 zeros. By comparison, the diameter of the Earth is about 12,700 kilometers. The diameter of our solar system out to the orbit of Neptune is about 9 billion kilometers. The distance from Earth to the nearest star, Proxima Centauri, is about 40 trillion kilometers. The diameter of the Milky Way is about 9.5 times 10 to the power of 17 kilometers. So, the Boötes Void is about 250 million times wider than our galaxy. It is about 77 trillion times wider than the distance to the nearest star. It is almost 240 quadrillion times wider than Earth's diameter. These numbers are essentially meaningless to the human brain as direct comparisons. Our minds evolved to navigate a world of meters and kilometers, of distances that can be walked or driven, of scales that fit within a human lifetime and a human field of vision. Numbers with 20 or 24 zeros are not really numbers to us in any lived sense. They are symbols that point towards something beyond direct experience. And that is fine. That is honest. The appropriate response to these scales is not to pretend we can picture them, but to acknowledge that the universe contains things that exceed our capacity for direct visualization. The Boötes Void is not a smaller version of something we can hold in our hands. It is a different order of thing entirely, a feature of the universe that exists at a scale for which human intuition has no template. What we can do, and what these comparisons are really for, is to create a sense of the ratios. The gap between the Boötes Void and our galaxy is as large, relatively speaking, as the gap between our galaxy and a single atom. We are not at the center of the scale of things. We are a particular size that happens to be the size at which we exist, sandwiched between the microscopic and the cosmological, neither the smallest things nor the largest, but one particular scale in an enormous range. The Boötes Void is not simply a large version of things we know. It is qualitatively different, a feature of the universe that only makes sense at scales so remote from daily experience that approaching them requires a deliberate slowing of the mind. That slowing, the willingness to sit with numbers that resist intuition and images that exceed experience, is part of what makes thinking about the universe an exercise in humility as much as curiosity. The walls of the Boötes Void deserve attention in their own right. The void is defined by what is absent from its interior, but it is bounded by regions where matter has been concentrated, the filaments and walls of galaxies that form its edges. These walls are as extraordinary in their own way as the void they enclose. When astronomers map the boundaries of the Boötes Void, they see galaxies concentrated into sheets and filaments that run along the void's edges. These concentrations are the regions where matter from the void's interior has been flowing for billions of years. In a sense, the walls of the void are the beneficiaries of the void's evacuation. The matter that left the interior went somewhere, and where it went was into the structures that now mark the void's boundaries. The filaments and walls at the edges of voids are among the densest structures
in the universe at their particular scale. They are not as dense as galaxy clusters, which are the most concentrated regions of ordinary matter in the cosmos, but they are significantly denser than the average cosmic density, and they are denser still than the void interiors from which the matter has flowed. In these filamentary structures, galaxies are more numerous, star formation is more active, and the interactions between galaxies are more frequent than in the void interior. The walls of the Boötes Void are, in this sense, places of relatively high cosmic activity. They are regions where the universe has been busy, where matter has gathered and organized itself into the structures that make the night sky interesting from within a galaxy. This contrast between the wall and the void interior is one of the most visually striking features when astronomers plot the three-dimensional distribution of galaxies around the Boötes Void. The boundary between the densely populated wall and the nearly empty interior is not perfectly sharp, but it is remarkably distinct. On one side, galaxies are present in numbers, consistent with the average cosmic density or higher. On the other side, they are almost absent. The transition happens over a relatively short distance in cosmic terms, making the void appear, in a galaxy map, almost like a bubble with a distinct boundary. This bubble-like appearance is not accidental. It reflects the dynamics of void formation. As matter flows outward from a void's interior, driven by the gravitational pull of the denser surroundings, the density gradient at the void's edge steepens over time. The void becomes more distinct from its surroundings, more sharply defined as it grows and empties. The result is that older, more evolved voids, like the Boötes Void, have relatively clear boundaries compared to younger, less developed voids that are still in the process of forming. The walls of the Boötes Void also serve as a kind of scaffold for the larger cosmic web. They are not isolated sheets of galaxies floating independently in space. They connect to other filaments and walls, to other voids, to the larger architecture of the cosmic web. The Boötes Void is bounded, and its walls connect to the surrounding structure. Understanding the void means understanding not just its interior, but its place in the larger web of which it is a part.
There is a question that may have been forming in the back of your mind as we have traveled through the Boötes Void and its surroundings. If the void is so large and so empty, could anything survive inside it? Not just galaxies, which we know exist in small numbers in the void's interior, but planets, life, observers? This is a question that crosses the boundary from cosmology into astrobiology, the study of life in the universe, and it has no certain answer. But the reasoning is interesting. For life, as we understand it to exist, you need at minimum a source of energy, which in most cases means a star and a planet with the right chemical conditions. A planet requires a solar system. A solar system requires a star. A star requires the gravitational collapse of a cloud of gas and dust. Gas and dust exist even inside voids, though in lower concentrations than in denser regions of the universe. The question is whether the conditions for star formation and planetary formation are sufficiently met inside the Boötes Void. The galaxies that do exist within the void demonstrate that star formation is possible there. Stars are forming inside those galaxies, even if at potentially different rates than in galaxies outside the void. If stars are forming, planets may be forming around them. And if planets are forming, the conditions for life are at least conceivable. But there is a more subtle issue. For rocky planets like Earth, for life based on carbon chemistry, you need heavy elements. Elements heavier than helium are made almost entirely inside stars through the process of nuclear fusion and dispersed into space when those stars die, either in supernova explosions or in gentler processes of stellar mass loss. The next generation of stars and planets incorporates these heavy elements, building up progressively more metal-rich environments over successive stellar generations. In a void environment where star formation may have proceeded at a lower rate than in denser regions, the enrichment of the interstellar medium with heavy elements may have been slower. The galaxies inside the Boötes Void may have lower metallicities, meaning lower abundances of elements heavier than helium than galaxies in comparable environments outside the void. This could affect the likelihood of rocky planet formation and, by extension, the likelihood of life as we know it. But there is another consideration. The galaxies inside the void have been evolving for billions of years, just like galaxies elsewhere. Even if their heavy element enrichment was slower initially, they have had a long time to build up those elements through successive generations of stars. The galaxies inside the void are not necessarily so metal poor that rocky planet formation is impossible. The honest conclusion is that we do not know enough about the specific conditions inside the galaxies of the Boötes Void to say with confidence whether life is possible there. What we can say is that the conditions are less favorable in some ways than in denser regions of the universe, and perhaps more favorable in other ways, given the relative isolation of galaxies within the void, which means fewer disruptive interactions and a more stable gravitational environment for any solar system that does form. If life does exist inside the Boötes Void, the experience of the universe from that vantage point would be profoundly different from ours. An observer inside the void would look out at a sky almost devoid of other galaxies at close range. The nearest neighbor galaxy might be tens or hundreds of millions of light years away. If that observer developed astronomy and cosmology, they would find a universe that appears, from their perspective, much emptier and lonelier than the universe as we experience it from our relatively rich cosmic neighborhood. They might wonder, as we do, whether they are typical or exceptional, and they would have a harder time answering that question than we do, because the void environment provides fewer nearby examples to compare to. The cosmic web would still be observable to sufficiently powerful telescopes, but the nearest filament, the nearest wall of galaxies, would be hundreds of millions of light years away. What would it do to a civilization's sense of itself to grow up in such a place, to develop science and philosophy in the context of a sky almost devoid of neighboring galaxies, to reach the stage of cosmic inquiry and find, looking outward, a darkness far deeper than what we see from Earth? These are questions without answers, but they are worth sitting with. They remind us that our cosmic address, our particular location in the web of filaments and voids, shapes the universe we can observe, and perhaps the kind of thinking we can do about it. Let us return to the mechanics of the void one more time and think about what is happening inside it right now, in the cosmic present, even though we cannot directly observe the present-day state of the void because of the light travel time. The matter that currently resides in the interior of the Boötes Void is engaged in a slow, persistent drift. Each galaxy within the void
is feeling the gravitational pull of the surrounding walls, the dense regions at the void's boundaries, where most of the nearby matter is concentrated. This pull is not strong on a per-galaxy basis because the walls are hundreds of millions of light-years away. But gravity is patient. Given enough time, even a gentle pull accumulates into significant motion. Over billions of years, the galaxies within the Boötes Void have been and continue to be drawn toward the void's walls. Their trajectories are gentle arcs, curving outward toward the higher density boundary regions. They are not falling rapidly. The timescales involved are enormous, billions of years for significant displacement. But the motion is real and persistent. This means that the interior of the void is becoming progressively emptier over time. Galaxies that are currently within the void are slowly but surely moving toward its edges. New galaxies are not forming in the interior to replace them, because the conditions for galaxy formation, the availability of dense gas clouds, and sufficient dark matter halos are not being replenished. The void is, in this sense, self-evacuating. The emptier it gets, the less gravity there is to resist the outward flow toward the walls, and so the process continues. Dark energy is also contributing to the void's evolution. Inside the void, where the density of matter is low, the effects of dark energy are relatively more prominent than in denser regions. In regions of high density, the gravity of the concentrated matter partially counteracts the expansion driven by dark energy. In the void interior, where there is little matter to provide gravitational resistance, dark energy more freely drives the expansion of space. This means that within the void, the local expansion rate of space is slightly higher than the cosmic average. The void is not just being evacuated by the flow of galaxies toward its walls, it is also being expanded more rapidly by dark energy than the surrounding overdense regions. This interplay between the gravitational flow toward the walls and the accelerated local expansion of space within the void creates a complex, dynamical picture. The void is evolving in response to both effects simultaneously, becoming both larger and emptier through different mechanisms acting together. One consequence of this is that the density contrast between the void interior and the surrounding walls increases over time. The void gets emptier relative to its surroundings, not just because matter flows out of it, but because the expansion of space within it slightly dilutes even the remaining matter further. The walls get denser as matter flows in. The gradient between them steepens. The void becomes more void-like as time passes. This self-reinforcing process is one of the reasons why supervoids, like the Boötes Void, are expected to become increasingly extreme features of the universe in the future. They are not heading toward some equilibrium state where the flow stops and the void remains stable. They are heading toward greater and greater emptiness, driven by gravity, dark energy, and the passage of time.
The relationship between voids and the cosmic microwave background is subtle but important, and it offers one of the most elegant connections between the largest empty structures in the universe and the oldest light in existence. The cosmic microwave background, which we have mentioned several times, is the radiation left over from the early universe, when it was about 380,000 years old. This radiation fills all of space uniformly, arriving at Earth from every direction with essentially the same temperature, about 2.7 degrees above absolute zero. It is the most perfect blackbody radiation ever measured. But it is not perfectly uniform. There are tiny temperature variations at the level of 1 part in 100,000 that encode the density fluctuations of the early universe. These fluctuations are the seeds of all the structure we see today. When photons of the cosmic microwave background travel through the universe toward us, they do not simply travel through empty space. They travel through the large-scale structure of the cosmos, through filaments and walls and voids. And as they do so, they interact with that structure through gravity. When a microwave background photon enters a void, it experiences the gravitational potential of the void. In a universe without dark energy, the void's gravitational potential would be constant over time, and the photon would lose as much energy entering the void as it gained, leaving it, resulting in no net change in its temperature. But in a universe with dark energy, the void is expanding over time, and its gravitational potential is becoming shallower. A photon entering the void at one potential depth exits it at a slightly different depth, resulting in a small net energy loss. The photon arrives slightly colder than it would have if no void were in its path. This effect, the integrated Sachs-Wolf effect, creates a small but measurable imprint on the cosmic microwave background. In the directions of large voids, the background should be slightly colder than average. In the directions of large filaments and clusters, it should be slightly warmer. By cross-correlating maps of the microwave background with maps of the galaxy distribution, astronomers can detect this effect and use it to study both the distribution of large-scale structure and the properties of dark energy. For the Boötes Void specifically, this means that looking at the microwave background in the direction of the void, we should see a slightly colder region. The signal is tiny, buried in the noise of other temperature variations, and detecting it requires careful statistical analysis. But it has been searched for, and some analyses have found evidence consistent with the expected signal. The power of this measurement is that it connects the properties of the void to the properties of dark energy. If dark energy is exactly as predicted by the standard model, a cosmological constant, the signal has a specific predicted magnitude. If dark energy behaves differently, the signal changes. Precise measurements of the Sachs-Wolf signal from known voids like the Boötes Void can therefore constrain the nature of dark energy in ways that complement other measurements. This is a beautiful example of how the most extreme features of the universe become tools for understanding fundamental physics. The Boötes Void, by virtue of its enormous size, produces a larger Sachs-Wolf signal than smaller voids. Its extreme character makes it more useful as a probe. The same property that makes it puzzling from a theoretical standpoint, its extraordinary size, makes it particularly valuable as an observational tool. It is worth stepping back from the specifics of the Boötes Void and thinking about what voids in general tell us about the universe as a living system. The word system is chosen deliberately. The universe is not a collection of independent objects scattered through space. It is a system in the sense that its components are connected to one another through gravity, through the flow of matter and energy, through the shared history of their origin in the Big Bang. Everything in the universe is related to everything else, however distantly. Voids are part of the system in a fundamental way. They are not passive gaps between the active regions of the cosmic web. They are active participants in the flow of matter and energy that defines the web's evolution. Matter flows into voids from the surrounding regions when the density fluctuation first forms, before the void develops. Once the void is established, matter flows out of it toward the surrounding walls. The walls, enriched by this inflow, develop higher density and attract more matter still. The cycle is self-reinforcing. In this picture, voids are essential to the structure of the cosmic web. Without voids, there would be no walls. Without walls, there would be no filaments. Without filaments, there would be no clusters. The web is a unified structure, and the voids are as much a part of its unity as the bright concentrations that draw the eye. There is also a sense in which voids drive the evolution of the web on large scales. The expansion of voids is one of the dominant motions in the universe, on scales of tens to hundreds of millions of light years. Galaxies near the boundary of a void are being pushed outward by the void's expansion, accelerated toward the walls. This outward push, the bulk flow away from void interiors, is one of the primary causes of peculiar velocity, the deviation of a galaxy's motion from the simple Hubble flow of cosmic expansion. When astronomers map the peculiar velocities of galaxies, they can infer the locations of voids and walls from the pattern of flows. Galaxies are moving away from voids and toward walls, driven by the gravitational physics we have described. The voids announce their presence not just through the absence of galaxies within them, but through the motion of galaxies outside them. They are gravitational repellers in a sense, regions that push surrounding matter away rather than attracting it, because their interior is less dense than the surrounding regions. This concept of voids as gravitational repellers is somewhat counterintuitive, because we usually think of gravity as attractive. But in the context of the cosmic web, what matters is the relative density, a region that is less dense than the cosmic average acts, in terms of its effect on surrounding matter, as though it were a negative mass, repelling rather than attracting. The surrounding denser regions attract matter more strongly than the void does, so matter flows away from the void toward those regions. The void does not push matter away by exerting a repulsive force. It simply fails to attract matter as strongly as its surroundings do, resulting in a net flow away from its interior. This is why voids expand over time, and why they are expected to continue expanding into the far future. They are regions where the gravitational balance of forces always works in the direction of evacuation, always drawing matter out rather than pulling it in. The Boötes Void, as the largest known void, is the largest known gravitational repeller in the observable universe. Its effect on surrounding matter extends over hundreds of millions of light years. Galaxies within that range are, on average, moving away from the void's interior at a rate that reflects the magnitude of the underdensity. The void is not just sitting there passively, it is actively shaping the motion of everything nearby. By this point in our exploration, we have covered the discovery of the Boötes Void, its size and emptiness, the physics that created it, the nature of voids in general, the galaxies within it, the walls that bound it, its effect on the cosmic microwave background, and its value as a cosmological probe. But there is one more aspect of the void that has not yet been fully addressed: its relationship to the concept of cosmic loneliness. Not loneliness in an emotional sense exactly, but in a physical, structural sense. The Boötes Void is a place of extraordinary isolation. The distances between objects within it are larger than in any comparable region of the universe. The nearest galaxy to any given point within the void is likely to be far farther away than the nearest galaxy to a comparable point in the filaments and walls. This isolation has a particular quality to it that goes beyond mere distance. In the filaments and clusters of the cosmic web, galaxies interact. They pass close to one another, disturbing each other's structure, triggering star formation, exchanging gas, sometimes merging into larger systems. This interaction is a kind of galactic community, a social fabric of gravity and gas and light that shapes the development of each galaxy in response to its neighbors. In the void, that community is absent. A galaxy in the interior of the Boötes Void has evolved largely without the influence of other galaxies. Its development has been driven by internal processes, by the physics of its own gas and stars and dark matter halo, rather than by the external stimulus of galactic interaction. It is, in a cosmic sense, alone. There is something philosophically resonant about this. The universe, in its densest regions, is deeply interconnected. Everything influences everything else. Galaxies shape one another. Clusters are shaped by their environments. The flows of matter from voids into walls connect regions hundreds of millions of light years apart. The cosmos is a web of relationships, and nothing within it is truly independent. But inside the Boötes Void, those relationships are attenuated to near vanishing. The galaxies there are still part of the universe, still subject to its laws, still connected to the larger web through gravity and the expansion of space. But the strength of those connections is far weaker than elsewhere. The cosmic community is present in the void, but at the level of a whisper rather than a conversation. Whether this isolation is a limitation or a kind of freedom depends on perspective. A galaxy evolving in isolation is not stunted in any simple sense. It still forms stars, still burns its gas, still ages according to the same stellar physics. But its history is different, its record less complicated by the scars of interaction. The Boötes Void is the universe's loneliest place, and in that loneliness, it has a kind of integrity. Everything that has happened there, everything that has grown or collapsed or shone or faded, has done so on its own terms, without the intervention of galactic neighbors. The void's interior is a place where cosmic history has been written in a simpler hand. The subject of dark matter, which has come up several times in our exploration, deserves a dedicated moment of attention in the context of voids, because dark matter, the invisible substance that makes up the majority of the universe's matter, content, behaves in the void environment in ways that are both consistent with and revealing of its nature. Dark matter, by definition, does not interact with light. It does not emit light, absorb light, or reflect light. Its presence is inferred entirely from its gravitational effects, from the way it bends the paths of light through gravitational lensing, from the way it affects the rotation of galaxies, from the way it influences the formation and evolution of cosmic structure. Inside a void, like the Boötes Void, dark matter is present in lower concentrations than outside the void, just as ordinary matter has flowed out of the void's interior over time. Dark matter has done the same, drawn toward the denser walls by the same gravitational imbalance. The dark matter density inside the void is significantly lower than the cosmic average. But here is something interesting. While ordinary matter can be influenced by non-gravitational forces, by pressure, by radiation, by magnetic fields, dark matter can only respond to gravity. This means that ordinary matter and dark matter in the void environment evolve slightly differently. Ordinary matter in the form of gas can be compressed by pressure waves, heated by radiation, and pushed around by the energetic output of stars and black holes. Dark matter can none of these things. It falls purely under the influence of gravity. The consequence is that in the void interior, dark matter and ordinary matter may not trace each other with perfect fidelity. In the walls and filaments, where matter is being compressed and heated by various non-gravitational processes, ordinary matter can be somewhat displaced from the dark matter distribution. But in the void, where densities are low and non-gravitational forces are weak, the two components track each other more closely. The void, in this sense, is a relatively clean environment for studying the gravitational dynamics of dark matter. This has not gone unnoticed by cosmologists. Voids have been proposed as environments where the properties of dark matter can be tested, because the low density, low pressure environment strips away many of the complicating factors that make dark matter hard to study in denser regions. Some alternative models of dark matter, including models where dark matter interacts with itself or with dark energy in ways not present in the standard model, make predictions that differ from the standard model, specifically in the void environment. Measurements of voids, including the Boötes Void, can therefore serve as tests of dark matter physics in addition to tests of dark energy. The Boötes Void is large enough that it encompasses a significant volume of the universe at near cosmic average conditions for dark matter, conditions that are different from those in any galaxy, cluster, or filament. Studying the distribution of galaxies and gas within the void, and comparing that distribution to theoretical predictions for how dark matter should behave in such an environment, is one way of probing dark matter physics in a regime that is otherwise difficult to access. This is one more dimension of the Boötes Void's scientific value. It is not just an interesting structure, it is a laboratory for fundamental physics, providing conditions that cannot be replicated on Earth or studied in any other way. We have been thinking about the Boötes Void in terms of what it contains, what it lacks, and what its existence tells us about the physics of the universe. But there is a simpler and more immediate dimension that is worth honoring before we conclude. The Boötes Void is beautiful, not beautiful in the way that a sunrise or a painting or a piece of music is beautiful. Those are forms of beauty that depend on sensory experience, on seeing or hearing something that resonates with human emotion. The void is beautiful in a different way, in the way that an elegant mathematical proof is beautiful, or a well-designed experiment, or a philosophical argument that simplifies a complex question into a clear principle. It is beautiful in the way that surprising truths are beautiful. Here is a surprising truth. The universe, at its largest accessible scales, is mostly empty. The structures we tend to think of as defining the cosmos, the galaxies, the clusters, the filaments, the bright nodes of the cosmic web, occupy the minority of the universe's volume. The majority of space is void. The universe's architecture is built as much from absence as from presence, and the two are inseparable. You cannot have the web without the voids. You cannot have the voids without the web. The beauty of one requires the other. The Boötes Void, as the largest known void, is the most extreme expression of the universe's tendency toward emptiness. It is where the cosmos has been most thorough in its evacuation, most complete in its removal of the usual furniture of galaxies and stars, most committed to the state of nearly nothing that defines most of its volume. In being so extreme, it reveals something essential about the universe's nature. That essential thing is this: the universe does not prefer fullness. It does not naturally tend toward a state where all space is occupied by matter and light. On the contrary, its natural tendency, driven by gravity and dark energy, operating on the initial conditions of the Big Bang, is toward greater and greater differentiation. Matter concentrates in some places and abandons others. The result is a universe of extremes: brilliant clusters and dark voids, dense filaments and empty bubbles, rich environments and lonely wilderness. We happen to live in one of the rich environments, but the Boötes Void reminds us that the rich environment is not the whole story. The void is equally real, equally a product of the same physics, equally a part of the universe's truth. To understand the cosmos fully is to understand both its density and its emptiness, both the light of the filaments and the darkness of the voids. The Boötes Void is beautiful because it is true, because it exists, because it is the universe being fully itself, without restraint. At the largest scale, it can express that nature. And there is beauty in knowing about it, in the fact that small beings on a small planet, using light as their messenger and mathematics as their language, have found this enormous emptiness and given it a name. That is a form of beauty too, a human form, fragile and temporary, but real. The tools that astronomers use to understand the Boötes Void are evolving rapidly, and it is worth thinking about what the next generation of observations might reveal. The Vera Rubin Observatory, also known as the Legacy Survey of Space and Time, or LSST, is expected to survey the southern sky with unprecedented depth and breadth, imaging billions of galaxies and providing a three-dimensional map of cosmic structure far more detailed than anything currently available. This survey will map voids with much greater precision than current surveys allow, identifying their boundaries more sharply, finding more galaxies within them, and enabling much more detailed statistical analyses of void properties. The Euclid Space Telescope, launched by the European Space Agency, is designed specifically to study the large-scale structure of the universe, including the properties of voids. By measuring the shapes and distances of billions of galaxies, Euclid will produce one of the most detailed maps of cosmic structure ever created. The maps from Euclid will allow astronomers to study void statistics with precision that has not been possible before, testing cosmological models at a level of detail that current surveys cannot achieve. The Square Kilometer Array, a next-generation radio telescope, will be able to detect neutral hydrogen gas across vast distances, tracing the distribution of matter in a way that complements optical galaxy surveys. Radio observations are sensitive to gas that does not form stars, gas that is too diffuse to be detected in optical surveys. This means that radio surveys can probe the distribution of matter inside voids in ways that galaxy surveys alone cannot. These new instruments will not only refine our understanding of the Boötes Void specifically, they will provide vastly larger catalogs of voids of all sizes, enabling statistical analyses that can distinguish between different models of dark energy and dark matter with much higher precision. The Boötes Void will become one data point among many, placed in the context of thousands of other voids mapped with comparable quality. Future observations may also tell us more about the galaxies within the Boötes Void. Current surveys have found only a handful of galaxies within the void, but more sensitive surveys may find more, particularly faint dwarf galaxies that are too dim for current instruments to detect. The properties of these galaxies, their star formation rates, their chemical abundances, their dark matter, halo masses, will tell us about how galaxies evolve in extremely low density environments. There's also the possibility that observations in the next decades will shed light on the question of whether the Boötes Void is genuinely anomalous within the standard cosmological model, or whether it falls within the expected range of fluctuations. More detailed simulations of cosmic structure formation, calibrated against the improving observations, will produce better predictions for the expected distribution of void sizes. Comparing those predictions to the observed properties of the Boötes Void will sharpen the question of whether it represents a genuine challenge to the model or simply a rare but allowed fluctuation. The Boötes Void has been waiting, growing quietly in the darkness for billions of years, long before humans existed to notice it. It will still be there, growing larger and emptier when the next generation of telescopes comes online. The observations we make of it in the coming decades will add another layer to our understanding of this extraordinary feature of the cosmos. As we approach the end of our long exploration of the Boötes Void, there is a broader reflection that seems fitting. Throughout human history, one of the most reliable sources of perspective has been the contemplation of something vastly larger than ourselves. The mountains, the ocean, the sky on a clear night. These have always been places where the scale of the ordinary human world shrinks against a larger backdrop, and where something that might be called awe becomes available. Astronomy has progressively extended this perspective to scales that dwarf even the most impressive natural landscapes on Earth. The discovery that the Milky Way is a galaxy of hundreds of billions of stars, the realization that it is one of trillions of galaxies in the observable universe, the mapping of the cosmic web, the filaments and walls and voids that define the universe's architecture on its largest scales. Each of these discoveries has expanded the frame within which human beings understand their place in the cosmos. The Boötes Void is part of that expanding frame. It takes the concept of cosmic scale and applies it specifically to absence, to emptiness, to the space between things. It reminds us that the universe is not just large, but diversely large, that it contains not just immense structures, but immense absences, that the space between galaxies, which already stretches the imagination in the case of the distance between the Milky Way and Andromeda, can extend to a scale that makes that distance seem small. The effect of sitting with this knowledge is difficult to articulate, but many people who spend time thinking about the large-scale structure of the universe, including professional astronomers who work with these concepts every day, describe something that functions like a shift in perspective, not a sudden revelation, but a gradual reorientation. The everyday world does not become less real or less important, but it acquires a context, a background against which it can be placed. The concerns that loom large in daily life do not vanish against the backdrop of the Boötes Void, but they can be seen from a certain distance. This is not a new observation. Human beings have always used the contemplation of vastness
as a way of gaining perspective. What is new is the precision with which we now know the vastness. We are not guessing at the scale of the cosmos or constructing mythological frameworks to give it meaning. We are measuring it. We are building maps. We are calculating the properties of structures that contain the light of hundreds of millions of years of cosmic history. The perspective that comes from that is grounded in something real and verifiable in a way that earlier forms of cosmic contemplation were not. The Boötes Void is real. It is there, in the direction of the constellation Boötes, hundreds of millions of light years away, nearly 1 billion light years across, by some measures growing quietly as it has grown for most of the universe's history. It is not a metaphor or a thought experiment. It is a feature of the universe that we have measured and mapped as best we can with the tools we have. And knowing it is there, knowing its approximate size and structure and history and future, changes something about how the universe feels. It makes the universe feel more completely understood, even as it reminds us how much remains unknown. This is perhaps the most valuable thing that contemplating the Boötes Void offers. Not comfort in a simple sense, not the reassurance that everything is fine, but something deeper, the sense that the universe is genuinely, materially, extraordinarily large and complex and strange, and that we have the capacity, through science and imagination and the patient accumulation of knowledge, to approach that strangeness and see it clearly. That capacity is remarkable, and the universe, with its voids and filaments and clusters and all the rest, is remarkable too.
There is one final thought that the Boötes Void invites, and it is perhaps the quietest one. The void is silent, not in the sense that sound does not travel through space, which is true, but beside the point. Silent in the deeper sense that nothing happens there in the way that dramatic cosmic events happen in dense regions. No supernova light up the interior. No black holes shred nearby stars. No cluster mergers send shockwaves of superheated gas through the region. No active galactic nuclei pour jets of energy into the surrounding medium. Inside the Boötes Void, the universe is simply there, in its most undramatic form. Thin gas drifting slowly, a handful of sparse galaxies moving gently toward the walls, dark matter distributed thinly through a vast volume, the cosmic microwave background threading everything with its ancient, uniform warmth, and space itself expanding, slowly, relentlessly, almost imperceptibly, but always. This silence, this undramatic persistence, is a kind of patience that the universe rarely shows so clearly. The dramatic events that define much of astronomical observation, the supernovae, the mergers, the quasars, all of these are expressions of the universe's energy and dynamism. But the void is the universe at rest, or as close to rest as the universe ever comes, a place where time passes and almost nothing happens, because there's almost nothing there to happen to. And yet, it changes. The void grows. It has been growing for nearly 14 billion years. In that growth, slow and quiet and persistent, there is a kind of statement about the nature of the cosmos that is easy to miss if you are only looking for the bright and dramatic events. The universe's dominant feature, in terms of volume, is not activity. It is stillness, not absolute stillness, because the expansion of space is always happening, and matter is always flowing, but relative stillness. The void is the universe's default, the state to which space returns when matter is absent, and in that state, the universe is simply there, enormous and patient and dark, awaiting whatever comes next. What comes next, over the very long term, is more emptiness. The voids grow. The cosmic web stretches thin. Dark energy drives the expansion faster and faster. Eventually, on timescales that dwarf the current age of the universe, even the walls that bound the Boötes Void will dissolve, and the distinction between void and not void will fade. The universe will become, in a sense, all void, but that is a very long time away. For now, the Boötes Void exists as a distinct thing, a definable absence within a universe that is, in other places, richly present. It holds its shape, more or less, against the background of the cosmos. It does its quiet work of growing and evacuating and imprinting itself on the light that passes through it. And we have spent time with it tonight. We have thought about it carefully, let its dimensions settle in our minds, followed its history back to the earliest moments of cosmic time and forward to its distant future. We have understood, as best we can, why it exists and what it tells us about the universe. That is not nothing. In a universe that contains a void 330 million light years across, the act of noticing it, of studying it, of spending an hour thinking about what it means, is a small but genuine contribution to the universe's self-awareness. The void does not know itself. We know it a little, and that knowing is what science is for. The night is quieter now. The images of the Boötes Void can settle into the background of your awareness, joining the other pieces of the cosmos that you carry without needing to actively think about them. The knowledge that this enormous emptiness exists, that it is out there in the direction of Boötes, growing slowly in the dark, is now part of your understanding of the universe. That understanding does not require you to hold all the numbers at once. The 330 million light years of diameter, the 2 trillion galaxies in the observable universe, of which only a handful inhabit this void's interior, the billions of years it has taken to grow to its current size, the billions more it will take to grow further still. These are not meant to be carried consciously. They are meant to be absorbed the way you absorb the smell of rain or the sound of a distant train. Part of the background of awareness, adding texture and depth to the world without demanding active attention. What the Boötes Void offers in its quiet and enormous way is perspective, the kind that does not diminish daily life but contextualizes it, the kind that says, not with words, but with sheer scale, that the universe is large enough to contain everything, including the emptiness that makes the presence of things more visible. You are here, in this moment, in whatever room or place you occupy. The void is out there, growing quietly in the direction of a constellation most of us can barely locate in the night sky. Between you and it are hundreds of millions of light years of space, filled with galaxies and filaments and the thin gas of the intergalactic medium, and threads of dark matter, invisible to any instrument we possess. All of it is part of the same universe. All of it is related through the shared physics of gravity and expansion, and the quantum fluctuations that started everything. And all of it is, in the deepest sense, yours to contemplate, not yours to own or control, or even fully understand, but yours to think about, to sit with, to let inform the way you see the world and your place in it. That is the gift that the Boötes Void offers, and that science more broadly offers. Not certainty, but clarity. Not answers to all questions, but better and more interesting questions. not the end of mystery, but a deeper acquaintance with it. The largest void in the universe is out there. It has been there for most of time. It will be there long after tonight. And we know about it, at least a little. That is something. That is quite a lot. If this slow journey through the universe's most extraordinary absence has been a companion for your evening, you might find yourself returning here again. There's always another question at the edge of what we know, always another part of the cosmos to explore at the pace of a slow breath, with the lights low and the night settling in. Rest now. Let your breathing find its own rhythm. The Boötes Void is growing quietly in the dark, and the universe is vast and patient and full of things worth knowing. Good night. There is something we have not yet fully addressed about the Boötes Void, something that sits in the background of everything we have discussed and deserves its own moment of attention. That is the question of time. Not the age of the void, which we have touched on, but the way the void relates to our perception of time itself. Every observation in astronomy is, at its core, an observation of the past. When we look at the sun, we see it as it was 8 minutes ago. When we look at the Andromeda galaxy, we see it as it was 2.5 million years ago. When we look at the light from the walls and boundaries of the Boötes Void, we are seeing those structures as they were hundreds of millions of years ago. The void we describe is not the void as it exists today, in the cosmic present. It is the void as it was when the light, now reaching our telescopes, first left those distant regions of space. This is not a flaw in our observations. It is an intrinsic property of the universe, a consequence of the finite speed of light. Because light travels at a fixed speed, looking farther always means looking earlier. The farther the object, the older the light we receive from it, and the earlier the epoch of cosmic history we are seeing. For the Boötes Void, which is roughly 700 million light-years from Earth, at its center by some estimates, the light we receive from its environs left those regions perhaps 600 to 800 million years ago. That was during the Cryogenian and Ediacaran periods on Earth, long before the Cambrian explosion of animal life, before the first fish, before any creature had developed eyes capable of looking at the night sky. The universe visible to our telescopes in the direction of the Boötes Void is therefore a snapshot of a moment in cosmic history that predates much of the history of complex life on our planet. This temporal dimension gives the Boötes Void a different kind of depth than its spatial extent alone suggests. It is not just large, it is ancient. Or rather, we are seeing it in its ancient state, as it was during an early chapter of Earth's biological history. The void that we map with current surveys is a historical document, a record of what the large-scale structure of the universe looked like at a specific moment in time. And in the time since that light left the void's boundaries, the void has continued to grow. Matter that was at the edge of the void hundreds of millions of years ago has since moved farther toward the walls. Galaxies within the void have continued their slow drift outward. The void is larger now, in the cosmic present, than the light we observe would suggest. We are always looking at the past, and the past is always smaller than the present for a growing structure. This creates an interesting challenge for astronomers trying to characterize the true current state of the Boötes Void. They must take the observed distribution of galaxies, which reflects the state of the void hundreds of millions of years ago, and use models of void evolution to infer what the void looks like today. This is not a straightforward process. It requires assumptions about the physics of void growth, the distribution of dark matter, and the behavior of dark energy. But it is the only way to estimate the present state of a structure so distant that direct observation of its present state is physically impossible. The Boötes Void is therefore, in a deep sense, both a place and a time. It is a region of space, but it is also a moment in the history of the universe, preserved in light and sent across the cosmos to arrive at our telescopes now. When we study it, we are doing more than mapping an empty region. We are reading a historical record, a chapter in the long story of how the universe's structure has evolved. Thinking about the Boötes Void as a historical record invites a comparison to other forms of deep history that we access through different kinds of evidence. Geologists read the history of the Earth in its rocks, the layers of sediment, the composition of minerals, the patterns of magnetization in ancient lava flows. All of these encode information about conditions on Earth millions and billions of years ago. By reading this record carefully, geologists can reconstruct the ancient geography of continents, the chemistry of ancient oceans, the temperature of ancient climates. The rocks are a library, and the tools of geology are the methods of reading it. Paleontologists read the history of life in fossils, the shapes of bones and shells and impressions in ancient stone, preserve information about organisms that lived hundreds of millions of years ago. By studying these remains, paleontologists reconstruct the bodies, behaviors, and ecological relationships of creatures long extinct. The fossil record is incomplete, biased toward organisms with hard parts and favorable preservation conditions. But it is genuine. It contains real information about the past. Astronomers read the history of the universe in light. Every photon that reaches our telescopes has traveled across space from some source at some moment in the past. The distance it has traveled tells us how long ago it was emitted. The spectrum of the light tells us about the physical conditions at the source, its temperature, its chemical composition, its velocity. By collecting and analyzing this light, astronomers reconstruct the history of stars, galaxies, clusters, and the large-scale structure of the cosmos. The Boötes Void is one page in this cosmic library. It is a page written in the distribution of galaxies and gas at a particular epoch, hundreds of millions of years after the Big Bang. Reading it tells us something about how voids looked at that moment in cosmic history, how large they had grown, how empty they had become, how the cosmic web was arranged at that time. Comparing that to what we see in more recent cosmic history, and to what we see in the very early universe through the cosmic microwave background, gives us a picture of how the universe's structure has evolved over time. This is one of the most powerful things about the observational approach to cosmology. Because we can see to different distances, we can see to different times. A survey of nearby galaxies shows the universe as it is roughly today. A survey of galaxies at moderate redshifts shows the universe as it was a few billion years ago. Surveys of the earliest galaxies show the universe as it was when it was less than 1 billion years old, and the cosmic microwave background shows the universe as it was 380,000 years after the Big Bang. Together, these observations give us a time-lapse movie of the universe's history, each frame separated by hundreds of millions or billions of years. The Boötes Void contributes to this movie by providing a snapshot of the void distribution
at a particular epoch. It is one frame in the time lapse, one data point in the reconstruction of how cosmic structure has grown over time. In isolation, it is extraordinary. In context, it is part of a larger story of how the universe has organized itself over its nearly 14 billion year history.
Before we truly come to rest, there is one more dimension of the Boötes Void worth bringing into focus. It is a dimension that is easy to overlook when we are focused on the physics and the cosmology. But that is, in some ways, the most fundamental. It is the dimension of human curiosity. The Boötes Void was not found because anyone expected it. It was found because astronomers were systematically mapping the three-dimensional distribution of galaxies, following the data wherever it led. When the data pointed to an enormous empty region where galaxies should have been, they noticed. They checked their data, they ruled out instrumental errors, they refined their measurements, and they concluded that yes, there really is an enormous, empty region of the universe in the direction of Boötes. That process, that willingness to follow the data, even when it leads somewhere unexpected, even when the result challenges existing models and expectations, is the heart of the scientific enterprise. Science is not primarily about confirming what we already believe. It is about discovering what is actually there, whether it matches our expectations or not. The Boötes Void was a discovery that did not match expectations, and its discovery made cosmology richer and more interesting than it had been before. The scientists who found it, Kirshner, Umler, Schechter, and Schechtman, were doing something that required patience and rigor. Measuring the redshifts of large numbers of galaxies in a systematic way is not glamorous work. It is careful, methodical, and time-consuming. But it is exactly the kind of work that produces real discoveries, because it is the kind of work that does not pre-select for interesting results. You measure everything you can in a region of sky, plot the results, and see what is there. Sometimes what is there is what you expected. Sometimes it is something no one anticipated. The Boötes Void was an unanticipated discovery of the first order. It changed how astronomers thought about the large-scale structure of the universe. It contributed to a revolution in cosmology that unfolded over the following decades, as more and more evidence accumulated that the universe has a web-like structure on scales far larger than anyone had imagined. The ongoing study of the Boötes Void and structures like it continues in the same spirit of following the data. Each new survey adds more information. Each new analysis refines the picture. Each new comparison with theoretical models sharpens the questions. The science is not finished. The Boötes Void is not fully understood. There are aspects of its size, its depth, its relationship to the standard model that remain subjects of active debate, and that is exactly as it should be. Science is not a museum of settled facts. It is a living process of inquiry, constantly updating and refining the picture of reality that it constructs from observation and reasoning. The Boötes Void is a subject of ongoing inquiry, which means it is not just a feature of the past, but a participant in the present and future of cosmological science. The human curiosity that found the Boötes Void in 1981, and that continues to study it today, is the same curiosity that drives all of science, the same impulse that makes children ask why the sky is blue, and philosophers ask why there is something rather than nothing, and cosmologists ask why the universe has the large-scale structure it does. It is one of the most enduring and admirable qualities of our species, the desire to know,
to understand, to look at the world clearly and honestly, and follow the evidence wherever it leads. The Boötes Void is there because the universe put it there. Through physics, we know about it because human curiosity sent astronomers out to measure the distances to galaxies in a systematic way and notice what was not there. The void and the curiosity are both part of the story, and the story is not finished.
The sky above you tonight, whether you can see it or not, contains the direction of Boötes. Perhaps the constellation is above the horizon, perhaps below it. Perhaps the sky is clear, perhaps clouded, but the void is there, regardless of whether the sky is visible. It has been growing for billions of years, and will continue to grow for billions more, indifferent to the hour, indifferent to the weather, indifferent to whether any conscious beings are thinking about it or not. That indifference is not cold. It is simply the way the universe is. It does not need our attention. It does not require our understanding. It proceeds according to its own physics, its own laws, its own deep logic of gravity and expansion and dark energy and the initial conditions set by the Big Bang. We are, in the grand scheme of things, a very recent and very small addition to the universe's story, and our awareness of the Boötes Void makes no difference to the void itself. But our awareness makes a difference to us. To know about the void is to have a larger sense of the universe we inhabit. To understand its origins is to have a deeper understanding of the physics that governs all matter and energy, including the matter and energy that make up our own bodies. To study its properties is to learn about dark energy and dark matter and the evolution of cosmic structure. To contemplate its silence and its patience is to gain a perspective on the scale of time and space that is genuinely enlarging. We are the part of the universe that knows about the Boötes Void. We are the part that has measured it and named it and thought carefully about what it means. In a cosmos of enormous emptiness and scattered islands of light, we are one of the islands, and we have looked out from our island and seen the darkness between the others, and we have not been simply overwhelmed by it. We have tried to understand it. That is remarkable. It is, by any measure, one of the more extraordinary things happening in this corner of the observable universe at this particular moment in cosmic history. A small species on a small planet in a modest galaxy within a moderately rich part of the cosmic web has developed the tools and the will to map the largest known empty region of the universe and to reason about why it exists. You are part of that species. You've spent time tonight thinking about the Boötes Void. That thought, however brief and however incomplete, is a contribution to the ongoing human project of understanding the cosmos. It matters, not in the way that the void matters, not at the scale of hundreds of millions of light years, but in the more immediate and personal way that awareness always matters, because it changes something in the mind of the person who has it. Let that change be a gentle one, not overwhelming or destabilizing, but quietly enriching. The world you return to after this exploration is the same world it was before, but you know something now that you perhaps did not know before, or did not hold so clearly in mind. And that knowing, however small, is part of what makes us the kind of creature we are. The Boötes Void is out there, enormous and quiet and dark. We are here, small and warm and momentarily aware, and between us, stretching across hundreds of millions of light years, is the universe itself, ancient and vast and full of things worth knowing. Sleep well tonight.
The void will keep. Good night.
There is a final image worth holding before this exploration fully comes to rest. Imagine a cartographer in the age of exploration, working without satellites, without radio, without any of the instruments we take for granted today. They have a ship, a compass, a sextant, and the skill to read the stars. They are charting unknown coastlines, filling in the blanks on a map that is mostly speculation and guesswork. Every new bay they discover, every new headland they chart, every new measurement they take, adds a small piece of real knowledge to a picture that is being constructed inch by inch, voyage by voyage, generation by generation. The astronomers who discovered the Boötes Void in 1981 were doing something analogous, though at a scale the historical cartographers could not have imagined. They were charting the universe, filling in the blanks on a map of cosmic structure that was, at the time, mostly speculation. Their instrument was not a sextant, but a spectrograph, measuring not the angles of stars above the horizon, but the redshifts of galaxies hundreds of millions of light years away. And the blank they filled in was not a new bay or an unknown coastline, but an enormous, empty region of space, a feature of the cosmic map that no one had known was there. The legacy of that voyage is still unfolding. Every new survey that maps more galaxies in and around the Boötes Void, every new simulation that models the physics of void formation, every new observation of the cosmic microwave background that looks for the thermal imprint of the void's emptiness, is another step in the same project. The map is being refined, the picture sharpened, the questions clarified. The Boötes Void is still being charted, and just as the age of exploration eventually revealed that the world was fully mapped, the age of large-scale cosmic surveys will eventually produce a map of the observable universe that is, if not complete, at least detailed enough to characterize all the major structures within it, all the filaments, all the clusters, all the voids. The Boötes Void will take its place on that map as the largest known void, surrounded by context that we are still developing the tools to provide. When that map is more complete, the universe will feel, in some sense, more known. Not completely known, never completely known, because the observable universe contains more galaxies than any survey can catalog in detail. And beyond the observable horizon lies a more universe still, but more known than it is today. The picture will be sharper, the questions more precisely posed, the answers more firmly grounded in evidence. And the Boötes Void will still be there on that map, larger by then than it is now, even emptier, even darker, still growing in the patient way that voids grow on timescales that make the entire history of human civilization seem like a momentary flicker. The void is patient. We can afford to be patient too. There is no urgency in contemplating the Boötes Void, no deadline by which we must understand it completely, no test to pass, just the slow, ongoing work of looking and measuring and thinking and refining the picture, carried forward by the same curiosity that first noticed an unexpected emptiness in the galaxy maps of the 1980s. The universe offers that much, at least, the invitation to keep looking, to keep asking, to keep refining the map of what is there and what is not. The Boötes Void is one of the most extraordinary features on that map, and we have spent time with it tonight in the quiet, at the end of a day, letting its dimensions settle and its history unfold and its future come into tentative view. That is enough for one night, more than enough. The void will be there tomorrow. good night.